Hey YouTube, today I will do topic modeling with the transformer based and as of now the most powerful tool called BERTopic. And I will apply BERTopic on a pretty famous dataset called arxiv abstracts to get the most important topics from that dataset. So first, a quick introduction on BERTopic. So BERTopic is a topic modeling technique that leverages transformers and class-based TF-IDF to create dense clusters, allowing for easily interpretable topics whilst keeping important words in the topic descriptions. And BERTopic supports guided, semi-supervised, and dynamic topic modeling. It even supports visualization similar to the very powerful package LDAVs. And BERTopic actually generates document embedding with pre-trained transformer-based language models, cluster these embeddings, and finally generates topic representation with the class-based TF-IDF procedures. And in this picture, what you see, they are the key algorithms that are used by BERTopic. So there are three main algorithms here, which is about first embedding the documents, then clustering topics, and then create topic representation from the clusters. So first about the embedding documents. Here, what BERTopic does is extract document embeddings with sentence transformers. Since the data we are working with are article titles or article abstracts, we will need to obtain sentence embeddings, which BERTopic lets us choose conveniently from among many sentence transformer models that are available. And then these cluster topics into semantically similar clusters. So here BERTopic create groups of similar documents with UMAP to reduce dimensionality of embeddings and HDB scan to identify and cluster semantically similar documents. And lastly, the last algorithm used by BERTopic is creating topic representation. So here it extracts and reduces topics with class-based TF-IDF. And TF-IDF, probably you already know that it allows for comparing the importance of words between documents by computing the frequency of a word in a given document and also the measure of how prevalent the word is in the entire corpus. And now if we instead treat all documents in a single cluster as a single document and then perform TF-IDF, the result would be important scores for words within a cluster. The more important words are within a cluster, the more representative they are of that topic. Therefore, we can obtain keyword-based descriptions for each topic. This is super powerful when it comes to inferring meaning from the groupings yielded by any unsupervised clustering technique. And here is the mathematical formula for class-based TF-IDF. So the frequency of each word T is extracted for each class I, that's why it is represented as Ti, and divided by the total number of words W, and also here Wi. So the average number of words per class represented by M here is divided by the total frequency of word T across all N classes, and that's why here we are summing over Tj from Tj to N. And that's your class-based TF-IDF formula. So basically all these are already included and very well optimized within the BERTopic package that we are going to use. And I have to say pretty much from 2022 onwards, when the BERTopic came into was first published and the code was available, it has become the single most important topic modeling technique across pretty much every domain. So if you are into topic modeling, you have to use this. Alright, so with that introduction, now let's get into the dataset that we are going to use for this topic modeling here. And the dataset is a huge collection of arxiv publications. And what they are saying is, for nearly 30 years, arxiv has served the public and research communities by providing open access to scholarly articles from the vast branches of physics to the many sub-disciplines of computer science to everything in between. Okay, let's actually look into the dataset. So remember, when you can download the dataset from here, and it is going to be a single file of a huge .json format. So these arxiv dataset and a metadata of 1.7 million plus scholarly papers across STEM discipline. This is the dataset about. So this is the .json file that I was talking about. It's 3.5 GB, and as you can see here, so this is a single entry in that .json file. So let's look at the first item here. So I have JSON format here. It's a dict format, and so each of these keys, so there are quite a few keys, and for example, I have ID, submitter, authors, title, comments, journal ref. For example, this key journal ref, that will contain the year of the publication, and that also is given with lot of extra string. So I need to take the last 4 digit to get the year of publication. And similarly, I have categories, that is a string, and it is given in a short form HEPPH, and we will see in a second that how we can get sense of these short form of categories, because if we go to arxiv's official side, they have given a detailed API where each of the short form of categories are expanded, and we can get the full form of these, and we actually need that to do this topic modeling. And here the important stuff, abstract. So this is the whole abstract of the first research publication, a fully differential calculation in perturbative quantum chromodynamics. Okay, I don't understand this text. This is abstract of the research paper for this very first item in the .json file. And obviously, I will put a link of the dataset in the notebook, which is available in the description of this video. That is in my GitHub repository. So first thing you have to install is BERTopic, and that's what I'm doing here. And then first thing I am going to do is to read the huge .json file with Dask, because Dask is relatively faster compared to Pandas. And also remember these for this dataset, the great thing about using arxiv abstract is that the text is typically well structured and very nicely, concisely written. So for BERT-based embedding models, this kind of concise text allows the document representation to be a bit more accurate than what we would normally see. So that's a good thing about this dataset. And the first thing, I have already imported import docs.bag as db, and also import JSON. And now let me read this .json file with Dask. So docs. Oh, have I think I need to just define this data file variable to be the source.json file, and that's my data file. Okay, and here. I just want to get the count of all the elements in the JSON file, and count.compute. So that's one of the method of Dask. It's an optimized. So what I have to give to compute is optimized graph, scheduler, optimization, but these are all optional. So just compute should be enough. So compute turns a lazy Dask collection into its in-memory equivalent. For example, a Dask array turns into a NumPy array, and a Dask data frame turns into a Pandas data frame. The entire dataset must fit into memory before calling this operation. Okay, this is something to keep in mind. This is quite a large dataset, 3.5 GB almost. But anyway, Kaggle gives you 12 GB of RAM, so that should work. I have already run the cell. It's taking kind of almost a minute to run it. But in the meantime, let me define a few more things. So I am going to use Plotly plot. Okay, it is still running. All right, just finished running, and this has the file. Our JSON file has 21,031,061 elements. That's a huge number of articles published in there. Okay, so now I am also going to check the top submitters in the publication. So for that, I'm going to use a lambda function. Submitter was the name of that key. So I am going to take from there the top 10 frequencies. True. This also going to take a little while, and frequencies, yeah, it should work. And these are the top submitters. We have the first one is just none, so that is a mixture of submitters. That is not important data point here. So the top submitters are EPTCAs, the CMS collaboration, Atlas publication, etc. Yeah, so that was just some basic information I fetched from the dataset. Now I am going to go to my VS Code to write some code. Okay, so this list, the one that you see currently, that's what I got from the arxiv official API documentation. The link is given here, right here. So there they have, just like I was saying, they have given the full name of these various terminologies for the category column in our data set. So for example, astroph means astrophysics. So what was the thing that we were seeing in the very first one? So we had HEP-PH. Let's see. So that's for high energy physics phenomenology. So this category name is what I need to get. So now, right now, I'm going to write a little util function to pre-process and prepare the data. What was the name? Data. Wow. A line in F, yield. Note that the JSON file in the dataset are huge, and sadly Python has certain memory problem when loading huge JSON file, and that's the reason that I'm using yield here. And next I am going to do just print the very first data point from my data. So each of these element in the JSON file actually represent a published paper. So that's what I am looping over right now for paper in metadata. Loads. Items. Print F. And immediately after printing the very first one, just break from the loop. That should do. And when I ran this cell, this is the output. This just outputted the very first element from the data. So I have starting with ID and then journal ref, comments, abstract, category, etc. Okay, so now I am going to extract all abstracts published between 2000 and 2021, and also their titles and the years in which they were published, because my topic modeling will be based on these published paper between 2000 and 2021. So I'm first just I'm declaring some list variable which will hold these things: title, abstracts, years, categories. Okay, and now looping over for paper in metadata. Reference will be the year, public journal ref. Wait. I need to get the value, so year should be the as we saw in the original data, the last four element of journal reference, that's represent the year. So I need to get the last four characters. And now a little if condition, because the paper should be published between 2000 and 2021. Categories dot category map is this long variable, long dict. Paper dict. Split by a single space and take the 0th element. Sorry, I made a syntactical mistake here. Paper dig.get, and my list is ending here. Let's print the title. Abstract, and also the categories. And this is output that I get for the length of title, abstracts, and categories, and they are all 1,049,158. So that many research papers published between 2000 and 2021. All right, so with that, I'm ready to actually train my BERT model, because all the important parts that is required to feed the BERT model, that is all the abstracts of all the papers, are already in these abstracts variable, because this abstracts variable is actually a list, and that's what list of text, and that's what is needed to be supplied to BERTopic for training it. So let's start that. And also note that I'm going to make sure that the minimum topic size of our topics is 50, and I do this to limit the number of topics that could be generated. For example, if the minimum were to be 10, then much more topics could be generated that are most likely to be of little interest. Since we want large topics, I set it at 50. So let's actually from BERT top. Yeah. True. Embedding model. So for the embedding model, you can select from a whole list of sentence transformer model that has been very well explained in the BERT's official documentation. So there are almost like 20-30 sentence transformer model you can choose from. And for this one, I'm going to choose a pretty relatively large one called all MPNet base v2. And we can actually see the model card of this one in HuggingFace. But let me complete this sentence first. And mean topic size, I'm going to keep it at 50. And this is the model card in HuggingFace for all MPNet base v2. So this is a sentence transformer model. It maps sentences and paragraphs to a 768-dimensional dense vector space and can be used for tasks like clustering or semantic search. Yeah, so that's and the model size, you can see the PyTorch.model.b, it's 438 MB, so rather manageable. So with this line, I just defined the BERTopic class to be used here, an instance of the BERTopic class indeed. And next, I actually have to apply the fit transform on this model. So topics, and these are the output from the training. Topic model dot fit transform. That's the function that will train it. So this this will take a list of documents to fit the models on a collection of documents, generate topics, and return the docs with topics. Arguments, documents, a list of document to fit on, embeddings, pre-trained document embeddings. This can be used instead of the sentence transformer model. And Y is the target class. So in this case, the first one will be abstracts. That is the only argument that I'm going to provide. The rest it will select by default. And for the embedding, I have already defined it here. So when we run this cell, that's going to take almost like 25 minutes or so with a 16 GB GPU. So yeah, be patient here. And while it's training, let me carry on with the next set of codes, because after the training is over, I am going to get the actual result, that is actual topics from the training. So I have to see those topics, and for that you use get topic info method. So topic model get, and these are all coming from BERTopic. You can check their documentation. Also, I need to plot the topics. So my plotting will be visualize bar chart. To that you pass top and topics. Let's choose 9. All right, so after the training, this is the topics that were generated. And first, this -1 means that these are the outliers. So anything outliers are labeled as -1 in the topic column, and the rest are the actual generated topics. So for example, the 0 is collisions, AU, RIH, ion. Then topic 1 is dark universe, cosmological energy. Let's look at something. Topic 5, lattice, quark, quenched, nuclear pairing, etc. Remember, these are research papers, so all this language may not make sense immediately to you, because here the original dataset was arxiv published papers. And the next line that we wrote here was to visualize a bar chart, and this is our bar chart, topic word score. So we can see here a very finely represented topics and the most important words under each topic. So for example, topic 0 has the most influential word under this topic 0 was collisions, AU, RIH, ion, heavy. Then topic 1, dark, universe, cosmological energy, etc. And that kind of thing goes on. Topic 5, topic 4, topic 7, etc. So actually interpretation of these clusters is much easier if you are familiar with the content of the documents. For example, under topic 1, the most influential words for topic 1 are dark, universe, cosmological energy, matter. So to me, it looks like some sort of theoretical astrophysics related research paper that the topic 1 is representing. So this brings to mind a general question that for each topic we have generated something like 10 words that best represent the topic, but can we determine how many words represents a topic? Like, is 10 words sufficient? Can we already have just one word to represent a topic? And to investigate this particular area, we have a tool in BERTopic. So to understand the amount of words needed to have a sufficient topic representation, we can show the decline of term score when adding new terms. So the idea here is that for each new term that is added has a lower term score than the previous one. Since the first term added has the best score for the topic, and the score goes on decreasing when I add more and more new terms under the same topic. Eventually, we reached a point of diminishing return, which is very similar to the elbow method used in k nearest neighbor. So right now I'm going to show these declining with a plot. And that code is, I need to use method from BERTopic, which is called the visualize term rank, and I have to apply that on topic model. So it's just a single line, visualize, term rank. That is it. That is all. Everything is built in BERTopic. You just need to apply this method and you will see a beautiful plot. And if you look at the documentation of BERTopic, this is where I am, visualize term rank. So each topic is represented by a set of words. These words, however, do not all equally represent the topic. This visualization shows how many words are needed to represent a topic and at which point the beneficial effect of adding words starts declining. And that's the... Okay, let's go back to the official documentation once more. So it takes a log scale, whether to represent the ranking on a log scale. So by default, it's false. So I am going to see both without a log scale and with log scale. So this is a plot of these lines that visualize term rank, and here I'm looking at the actual scale. That is, I have not passed logarithmic scale as true. So we can see that here maybe keeping up to 7 is kind of okay, but after 3 it rapidly declines. That is, the first 3 words actually very much describes the topic. But now let's look at the logarithmic scale, because that will give a more realistic situation. And looking at this, looks like that it seems that the 3 words per topic are sufficient to represent the topic well. Any words that we add after that have seemingly little effect. And the next thing we are going to plot is this topic relationship. So intertopic distance map, and for that you just apply this topic model, visualize topic. So here, looking at this plot will tell you that which are the topics which are completely different, and some of the topics are actually kind of very overlapping, so they can actually be merged. For example, topic 20 and topic 6 here, they are almost similar, co-centric. So this plot actually maps our topics to a 2-dimensional representation by reducing the topic vectors with UMap. And it's pretty important, pretty useful to decide which topics to reduce your dimension further. That is, which topics you no more need in your modeling separately, or in your presentation, or in your ultimate decision making separately. Further few beautiful plots and useful plots you can build with BERTopic. For example, this one is visualize hierarchy, and it will show with these straight lines and also color coded the hierarchy between topics. And even more, let me see, what do I have? Okay, so I also have, you can also plot these heat map similarity matrix. So with visualize heat map, and you just pass the number of cluster and number of topics, and it will plot your similarity matrix between topics. And here in this heat map, some of the darker blocks actually represent the cluster of topics to be found that are somewhat or largely similar to each other. You can zoom in, and also if you hover your mouse over them, you can check their values. And for example, here in this block, the similarity score is pretty high, 0.87. And lastly, another very important plot you can do is plotting the topics over the time period, over the years. So although extracting the topics and their representation is interesting, we are missing some dimensional information, which is the time period. For example, some topics might not be relevant anymore, or some are gaining traction over the last years. And so that can be vital information when making your business decision. And for these plot creation, you only need 2 lines of code. That is all. So you already have our list of text, which is abstracts. We already have our topics, and you pass a time period here. So here I'm passing 10, which means it will create the topics over the past 10 years. And then you apply this method, visualize topics over time, to your topic model. Remember, again, this topic model is fully trained with the fit transform. So to this visualize topics over time, you pass these topics over time, these variable, and pass the top number of topics. I need 20. Width and height is just for plotting parameters, and this is a beautiful plot you get. And if you hover the mouse over these graphs, you will see the topic number. For example, the green ones was so important, so intense during the period of maybe 2005 to 2012. But eventually it declined drastically over 2012. So this is my topic 2. And similarly, more recently, this is topic 6, and this kind of was at the peak of its importance in 2020, and then also it declined quite rapidly. So yeah, these distribution over the time, over the past years is sometimes very, very important for your business decision. And the last class, or the last plot that I wanted to show here, is this one, topics per class. So I'm looking at the official documentation in BERTopic. So topic per class creates to create the topics per class, BERTopic needs to be already fitted one. That's obvious. From the fitted models, the C, TF, IDF representations are calculated at each class C. Then the C, TF, IDF representations at class C are averaged with the global C, TF, IDF representations in order to fine-tune the local representation. This can be turned off if pure representation is needed. So basically, what this topics per class is doing is that so when we do topic modeling, the number of topics are typically much larger, or relatively larger, than the number of categories that was already there in the dataset. And these topics per class helps us to find and understand certain subcategories that might exist in the data, and also specifically plot that how many topics were found out by these BERTopic modeling for each original categories that was there in the original data. And to get that, you just need 2 lines of code. So topic model dot topics per class, you apply this topic per class here, and to it you pass the abstracts. That's what the documentation needed. The first argument is a docs, which is a list of string, the documents you used when calling either fit or fit transform. Yeah. So that's what we are passing, and classes are the original categories in our document, in our original data set. Remember, the original arxiv had a category key, and that will show you the category. That is, whether it's astrophysics or whether it's hardware architecture, things like this. That is, these things I'm talking about. These are the original categories defined in the original data set. And then the next line of code, just this one, topic model that visualize topic per class. To that you pass these topic per class variable. I need top number of topics 10, width 900, and that's a beautiful plot you get. So you can see that under the astrophysics, number of topics is 0 word. So these are the topics under these astrophysics category. Similarly, under these mathematical physics, these are the topics. And as the official documentation says that these topic per class returns a data frame that contains a topic, words, and frequency of topics for each class. And that's what is plotted here. And you can also see the frequencies in the horizontal axis. So we can see the maximum number goes beyond 800 for these, I think that's plasma physics or information theory, maybe. Probably it is information theory. That's where the frequencies are highest. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So see you in the next one. Thank you very much for watching. Hey everyone, SetFit or Sentence Transformer Fine-Tuning. This new paper generated a lot of attention and lot of discussion over the last few days. So the official name of the paper is Efficient Few Shot Learning Without Prompts, and published by the researchers named over here. So this video will be a quick discussion around this paper and also the code implementation that HuggingFace has published. And the main reasons that SetFit generated so much attention is because it outperforms GPT-3 in few shot text classification. That is where labeled examples are 50 or less. And it is 1,600 times smaller and can be run on your CPU. So just going through the paper, what they are saying in the abstract is recent few-shot methods such as parameter fine-tuning and pattern exploiting training have achieved impressive results in level scarce settings. However, they are difficult to employ since they are subject to high variability from manually crafted prompts and typically require billion parameter language models to achieve high accuracy. To address these shortcomings, we propose SetFit or Sentence Transformer Fine-Tuning. And so few-shot learning methods have emerged as an attractive solution to level scarce scenarios where data annotations can be time-consuming and costly. These methods are designed to work with a small number of labeled training examples and typically involve adapting pre-trained language models for specific downstream tasks. And okay, let's go SetFit. Yeah, so this is where they are mentioning the main architecture and the mechanism of their approach. So SetFit is based on sentence transformers, which are modifications of pre-trained transformer models that use Siamese and triplet network structures to devise semantically meaningful sentence embeddings. The goal of these models is to minimize the distance between pairs of semantically similar sentences and maximize the distance between sentence pairs that are semantically distant. Okay, this is an important point. Yeah, so this is an important representation of their whole architecture. So SetFit uses two-step training approach in which we first fine-tune an ST. ST means the sentence transformer, and then train a classifier head. So in the first step, and sentence transformer is fine-tuned on the input data in a contrastive Siamese manner on sentence pairs. In the second step, a text classification head is trained using the encoded training data generated by the fine-tuned sentence transformer from the first step. Also, HuggingFace has published a great blog on SetFit. This is the one that I'm looking at currently, and there they have given these some benchmarking result, and these are really awesome. It's just almost unbelievable. So look at this cost comparison. So TFew 3 billion compared with SetFit, and the cost is 28x smaller, whereas the accuracy of SetFit is only minus 1.7%. So that kind of improvement in results you get. And since SetFit achieves high accuracy with relatively small models, it's blazing fast to train and on much lower cost. For instance, training SetFit on an NVIDIA V100 with 8 labeled examples takes just 30 seconds at a cost of 0.025. Unbelievable. By comparison, training TFU 3 billion requires an NVIDIA A100 and takes 11 minutes at a cost of 0.7 for the same experiment, a factor of 28x or more. In fact, SetFit can run on a single GPU like the ones found on Google Colab, and even train SetFit on CPU in just few minutes. As shown in the figure above, SetFit speedup comes with comparable model performance. Similar gains are also achieved for inference, and distilling the SetFit model can bring speedup of 123x. Alright. And the coolest part is that Huggingface has published these code in GitHub repository implementing SetFit. And this is that repo that I'm looking at, and they have also given some examples of actual Jupyter notebook where you can run it in Colab, and that the entire notebook will get executed only within probably 4 to 5 minutes. It is so fast. So this is the code repository that I'm looking at. That there's this trainer file which takes care of actually training the training pipeline, and then the important one is this modeling.py, this file. So referring back to the paper, the original architecture, as we just discussed, that SetFit uses two-step training approach in which we first fine-tune a sentence transformer and then train a classifier head. And that's exactly what you will see here. So this is that main class SetFit model, and if you go down, let's see. Yeah, so I have mainly two things. One is model body and then model head. And what is my model body? That's an instance of sentence transformer class here, defined within the from pre-trained method. And what is model head? That's defined here. So if you have a model head file, then this model head is just loading that one. Otherwise, model head is an instance of logistic regression. And also the paper and also the Huggingface blog talks about sentence pair generation for this model. As we read in the paper right in this section, that the goal of this model is to minimize the distance between pairs of semantically similar sentences and maximize the distance between sentence pairs that are semantically distant. So for that we have a couple of methods to for that area. So I have sentence pair generation here, initializes to empty list to hold the sentence pairs and labels to indicate if a pair is positive or negative. Then I also have sentence pairs generation for multi-label, and lastly I have sentence pairs generation cosine similarity. Okay, so if you read their blog, let's go to the blog. Yeah, so they mention here pretty clearly that SetFit takes advantage of sentence transformers' ability to generate dense embeddings based on paired sentences. In the initial fine-tuning phase stage, it makes use of the limited labeled input data by contrastive training, where positive and negative pairs are created by in-class and out-class section. The sentence transformer model then trains on these pairs or triplets and generates dense vectors per example. In the second step, the classification head trains on the encoded embeddings with their respective class labels. And at inference time, the unseen example passes through the fine-tuned sentence transformer, generating an embedding that, when fed to the classification head, outputs a class level prediction. Alright, now let's go to this collab that has been given as an example in their repository. So obviously first you need to install your SetFit, and then with the load dataset, you import load dataset and sentence transformer.losses or cosine similarity. Then you also import the relevant models from SetFit, and then load a dataset. Dataset load emotion. There are quite a few options here in the repository that HuggingFace has published. For example, I think there's you can load Amazon review, you can load a few other as well. So in the repository, if you go to utils.python file, these are the options that are given for running these examples. You can load SST2, IMDb, SUBJ, BBC News, Enron Spam, and US. So these are the options right now. And okay, so here we are loading the emotion dataset, and this is the emotion dataset. If I just let me print the dataset. So obviously it's a HuggingFace dataset dict format. So I have train, validation, and test. Under the train, I have 16,000, validation 2000, number of and test 2000, and it is a very simple dataset with just two features: text and label. Text is a text obviously, and label is just a numerical label of 0, 1 for binary classification. And then after loading the dataset, you select n example per class, and here n is 8. That is, you take 8 example per class, and we have 2 classes here, and that's why they're doing 8 multiplied by 2, and that's your train dataset. And also you have your test dataset, and that's pretty much it. And then you just define a model from setfit.pretrained, and you pass sentence transformer, paraphrase, mpnet, base v2. And obviously here, instead of this model, you can choose any from the sentence transformer package. And there's a whole plethora, a whole list of models you can choose from, and also many multi-language model you can choose, because SetFit is also producing awesome result even for multi-language situations. So just by switching these model name, that is a base model name, to a multi-language one, SetFit can function seamlessly in multi-language context. So in their experiments, they have found that SetFit's performance shows promising results on classification in German, Japanese, Mandarin, French, and Spanish in both in-language and cross-linguistic settings. Alright, so now that your model is defined, then you just create your trainer configuration by setting the parameters to SetFit trainer. Here it's a very simple one. You just define your train dataset, eval dataset, loss class as your cosine similarity loss, batch size, number of epochs, and number of iterations, and that's it. And then you do trainer.train. This line took something like, I think, 3 minutes or so to run for a single epoch. And yeah, that's just a simple example of checking SetFit on various dataset, and then you can also do trainer.evaluate for getting some evaluation metrics. Coming back to the paper, there's a few more informations about its overall benchmarking. Here is a table how SetFit MPNet and SetFit Mini LM is performing against TFew 3 billion. Another important and kind of interesting fact is that the storage cost of SetFit models is 163 times to 26 times smaller than T03B checkpoints. So TFew 3B takes 11.4 GB, whereas SetFit models take 70 MB or 420 MB. Awesome. So overall, for the benchmarking of SetFit, this is what the HuggingFace blog talks about, that although based on much smaller models than existing few shot methods, SetFit performs on par or better than state-of-the-art few shot regimes on variety of benchmarks. On Raft, a few shot classification benchmark, SetFit-Roberta, with 355 million parameters, outperforms PET and GPT-3. It places just under average human performance, and the 11 billion parameter TFew, a model 30 times the size of SetFit-Roberta. SetFit also outperforms human baseline on 7 of the 11 Raft tasks. Yeah, so looks like this is going to be a trend setter in natural language processing research. Hey YouTube, the subject of this video is predicting the customer reviews of Yelp by fine-tuning a HuggingFace model, pretty famous one called BERT-based uncased. And for the dataset, I am going to use the very popular Yelp review dataset from Kaggle. It's available from a variety of resources. You can actually download the original data, which is really huge, almost 10 gigabyte if you download directly from the Yelp, and that contains a lot of extra information. But this one in Kaggle, that's a much more concised version. So here the dataset structure is just a single .csv file of only 8 MB, and this is the data. So the main thing about the data is all these are column names: business ID, date, review ID, stars, text. Now for this exercise, I am just going to need these two columns: stars, which are the customer stars given by each individual customer, and text is actual review text. And so the basic problem set here is that this text is my actual feature and these stars are the targets. And the purpose, the problem that we have to solve here, that we have to, based on this text, we have to predict the stars given the text. So basically, we are going to split the dataset into train and test part, and then we will fine tune on the training part of the dataset, and then after the training is over, we will use a fine-tuned model to predict the stars on the test portion of the dataset. So, and you definitely need a GPU for this project because the BERT-based uncased model fine-tuning with CPU will be impossibly slow without GPU. But Kaggle or Colab GPU that they provide is more than enough for this exercise. So I am doing it in Colab. And the dataset I have actually saved in my Google Drive. So you have to mount your Google Drive in Colab with this code here. And for the GPU, you just run NVIDIA SMI to get your GPU configuration. And I got a T4, Tesla T4 with a 16 GB VRAM. That's more than enough. And obviously you have to install your transformers, tokenizers, etc. And these are just, I'm importing all the relevant modules. Okay, about just here mention about these three lines here, because here I'm importing all the codes from three separate Python file. So this is the main notebook where I will do the entire project, and you will show the outputs. But all the actual training code, modeling code, and data loader code will come from these separate Python files. And so this is the way normally I structure my project. In that way, these Python files can become modular and reusable for other projects as well. So that's why I'm whatever function or method I'm going to define in these three files, all of them I'm importing with these three lines. From data loader, import star. That means it will import all the methods from that file. And otherwise, these modules that you see right here, they are all standard imports. So I'm going to be using PyTorch for this project. So I'm importing all these data loader, dataset, and Optim, etc. from PyTorch. Then NumPy, Pandas, Matplotlib, sklearn, etc. And here just few more things. I'm defining the configuration for my sns.plot, and also I'm defining the random seed to be 42. And yeah, and device, if CUDA is available, use CUDA, otherwise CPU. Okay, first thing, just read the CSV file. Here actually I also downloaded the 9 MB file from Kaggle to my local machine. So here I'm reading it from my local machine, but obviously this path can be anything, any cloud machine that you are using. And when I read the dataset with Pandas, this is the form, and we can see business ID, date, review ID, stars, text, type, user ID. Now these two are the only two columns needed for this exercise today. The reason is the other columns are also important, and then you can do many feature engineering part because they also contain some intelligence, some information in them, and that could be included in the modeling. But this exercise is a baseline model, to see the fine-tuning of a Hugging Face model and how that can be used to predict the classification of a textual corpus. So I'm not doing any feature engineering in this project, otherwise it will also become super long, which I don't want. That's the reason for this exercise. I'm only going to need stars and text. Okay, now the stars, when I print the values of the stars with the let me zoom out a little bit. Values of the stars, you can see I get 1, 2, 3, 4, 5. That's the unique values I get from the stars given by the customers. Now there's one quick problem here. When I initially when I started modeling the project with these values itself, these are my class values actually, I got an error during the modeling part and during the loss calculation, which said something like CUDA runtime error, device side assert triggered. And after doing some research in Stack Overflow, I got to know that that device side assert was actually coming from, there could be a few areas where these problem could come, but most of the other users who have faced the same problem were guiding me towards making the classes a zero based one. And they were talking like that some loss functions have different ranges for the possible inputs that they can accept. If you choose an incompatible activation function for your output layer, it will trigger this error. For example, they said that BCE loss requires its input to be between 0 and 1. So in this case, this is a multi-class classification problem, and I'm going to use cross-entropy loss. And there also I faced a problem, so I just have to make these 1, 2, 3, 4, 5 to 0, 1, 2, 3, 4. That is a zero-based index. So I used this little function here, map sentiment score. Basically, if the star number is 1, return 0, star number is 2, return 1, and so on. And then with these apply method of pandas, I just reformatted or restructured the star numbers to zero-based index. So after doing this, I am going to read the df.head again, and also going to do these unique for method here again. And now we can see the unique values of the classes are just 0, 1, 2, 3, 4. That's what we wanted. Okay, now just to check the distribution of these star values, I'm going to plot a count plot with SNS. So before that, I am just also defining a variable class name. So we will need these class names down in the notebook as well during the modeling part. So class names is just a list of 1 star, 2 star. And then with sns.countPlot, I plotted this. Let me zoom out. So that's the distribution of our customer reviews. So we can see that most are 4 star and 5 star indeed. So that was our distribution. And remember, these text and star columns will be the feature. We already talked about this. Text will be our features and stars are our target, class target. And later we will define, I'm just mentioning it here just to keep the context. Later, before the modeling, we will define these 2 lines and make them into list so that you keep the context, the significance of these text and the targets. So reviews will become df.text.toList and targets will become df.stars.toList. All right, now I just am going to define a tokenizer using BERT base uncased. So this line is just doing that. BERT tokenizer from pre-trained and pre-trained model checkpoint. This is coming from, I have actually defined this line, I think here. So modeling.py file, that's where my BERT base uncased that's been defined. So that's my tokenizer. And now in the next cell, I'm just going to check that the tokenization and production of the producing the token IDs, etc. are working. So for that, I'm just defining a sample text, just an example single sentence. Text processing with machine learning is moving at a rapid speed. This is my sample text. And on that, I will create my tokens by doing tokenizer.tokenize. and with that you just pass sample text. And token IDs, to create my token IDs, you need another method from the tokenizer, which is convert tokens to IDs, because these tokens are actually strings, list of strings basically, and you want to see the IDs, the corresponding IDs. So you pass convert token to IDs and pass tokens to that. And then I'm just going to print my sample text, tokens and token IDs, and let's see the output. So this is my sample text, and these are the tokens which were generated from the sample text, and these are my token IDs. So all these IDs are actually kind of unique values identifying each of these strings. That's fundamentally it is. All right, with that, I also wanted to do apply these encode plus, because that's super important when you are working with tokenization, and we are going to use encode plus in our modeling as well. So let's see the effect of these encode plus. Actually, let's take these codes into a separate cell. Yeah. Okay, so we already have our tokenizer defined, and all I'm doing here, I'm actually doing encode plus. That's what you need to do before you feed them into your modeling. But here we are doing that only for a single sample sentence, but during our modeling, the entire training corpus will go through this process. And in the encode plus, you supply these parameters. You can just check out encode plus HuggingFace official documentation to know more about them. Mostly these are truncation equal to 2, padding equal to true. These are kind of almost standard you have to do in most projects. Of course, padding takes different values. It takes length, I think longest, and also yeah, there's another value it takes. I'm forgetting. I just need to check out the documentation again. And return tensor pt, because we are using PyTorch. Add special tokens true means it will add CLS and separator. And yeah, so let's check out after the encoding, let's check out the output. So we are first printing encoding.keys, and that will have our input IDs and attention mask. And then to check out the actual input IDs, you just do encoding input IDs and then take the 0th element, because the whole encoding will have two things. We'll have two keys actually, which we just saw. It will have input IDs and it will have attention mask. So to check out the input IDs, you just take the first element. So these are our input IDs. All right, another quick information before proceeding, that we have encode plus and also an alternative method called only encode. So the encode plus and encode, both of these methods tokenize your text and prepare them in a proper input format for the BERT model. So both gives you kind of similar result, that is both encode plus and encode. Only difference is that the encode plus gives you some additional information, specifically input mask. So this is the official documentation where you will find both the definition of encode and encode plus. So just check out what the tokenizer says. The tokenizer is in charge of preparing the inputs for a model. The library contains tokenizers for all the models. Most of the tokenizers are available in two flavors, a full Python implementation and a fast implementation based on Rust library. Okay, they are for some information. And if you go down, this is where you see encode plus. These are all the different parameters it takes. And yeah, so as we are saying, the padding, this parameter we have given true, it takes longest. Also it takes max length, which are pad to maximum length specified with the argument max length or to the maximum acceptable input length for the model if that argument is not provided. Okay, so I definitely recommend you go through these, because these are the most fundamental and you have to always use these for any Hugging Face or Transformer project. Anyway, coming back to our code, let's check out the next outputs. So that was input IDs, which we saw with this. And the next one, I am going to check out the attention mask, and that also you just print the attention mask like this, encoding attention mask, and that will give you a tensor like this with all one means where there are actual input tokens. That means attention needs to be given to those tokens, and if there are padding, then I will see 0 in those places. Also, the last printing is tokenizer that convert IDs to tokens, and then you pass the actual input IDs. So basically this will convert the actual input IDs to tokens. That means it is reversing the process, and by doing this we can get back the original tokens. Okay, next I'm just doing a little EDA of the token counts in the review dataset. So I'm just defining a token length list, which will contain the list of tokens and the length by just looping over df.text. So I'm just going through each of the rows in the my original data frame on the text column, and then just appending the length of the tokens to this token length list. So tokens will be equal to tokenizer.encode. That's how we get our tokens. And we are providing max length equal to 512 because that's the maximum length for BERT base uncased. And we are getting the length of the token by doing len tokens and appending that to token length list, and then just plotting it with sns.dist plot. And this is the plot I get. So on the horizon, let me just zoom out a little bit. On the horizontal axis, we have token counts, and on the vertical axis, it's the density. Yeah, so that's we can see that mostly 50 to 110 maybe, that's where the density is highest. Yeah, so that was just for looking at the overall token density, because look at this, after 250 it's kind of reduces, and remember 512 is the maximum sequence length or the maximum length for our BERT model that we are going to use. So looks like this distribution of the text here is kind of compatible and kind of will be well suited for our BERT based model. Yeah, so now just I'm going to split. I'm almost done with the basic pre-processing and etc. I'm just now going to directly go to the splitting the dataset. So here I'm using the very well-known trend test split from sklearn to keep 30% as test size, and also for the test side as well, I'm taking 50% division between validation and 50% for test. So overall 70% of the data is going for my training, and the rest 30% is getting divided equally between validation and test. All right, now that was in this file, and now I need to go to data loader to define a util method, because I cannot directly supply these df train or df val or to the model. I need to make use of data loader of PyTorch, because they are going to be fed into a deep learning model. So I need to provide them batch by batch. So data loader will take care of all those batch by batch supplying and feeding to the model. So let's go to data loader.py, and here I'm going to define a method. So as we discussed before, this is where I am making use of reviews as features, which is the text, and my targets are actually list of numerical values, which are the stars given by the customer reviews. That's my targets. Now this way of passing the data loader or generating the data loader for feeding into the model would have been enough, but that's not really the best practice because you may get some error in this way. So you actually need a data collator object here. So let me bring it from Transformer. Have I imported it already? No, I don't think so. So yeah, I need to import these data collator with padding, and then I need to define another collator object, which is that takes the same tokenizer, and padding, let's give it longest. Again, for padding, you have couple of options. Tokenizer, it says not defined because we defined the tokenizer in the main Jupyter notebook. So you pass these collator object through an argument called collator function. Yeah. And that's where our data loader functionalities are completely built. Yeah, so now let me generate a train data loader and validation data loader and also test data loader with this create data loader method in the main Jupyter notebook. All right, now that we have our create data loader method defined, so I can create the train, val, and test data loader by just supplying to this method my df train, df val, and df test respectively. All right, and now if you want to see what these, for example, val data loader has inside it, you just have to run a loop like this, and this will print a long list of dict keys like this. So each of these, when you loop over val data loader, each of the elements d.keys will give you input IDs, attention mask, targets, and review text. So that's how from these each of the data loader you get your input IDs, attention mask, and targets, and exactly what we need when we are going to build our next modeling class. Okay, so let's go ahead, and just to check that this data loader is working fine, you can print the keys and input ID shape like this. So that's what this cell is doing. So we already saw data.keys gives you this list, and then if you print the shape, data input ID shape, that will give you a torch tensor of 16 by 512. 16 because we chose a batch size of 16, and 512 is our max sequence length. All right, yeah, so now I need to build model utility class called sentiment classifier. So let's go to my modeling file. So this sentiment classifier is inheriting from nn.module, so I can get access to the methods of nn.module. Self. Now here is the important thing to understand, that what we are doing for building our classifier is I am taking the base model from BERT base uncased, and then that becomes my body, and on top of the body I am adding I will be adding a classifier layer that will be called the head, and that's following just a standard architecture of using transformer based models for downstream tasks, that you take a base model which becomes your body, and then on top of that you add your classifier head, or actually task specific head. In this case my task specific head is a classifier. It can be other tasks, for example it can be question generation, or it can be next sentence prediction. So I have a separate video in this Hugging Face related playlist in my channel, which specifically talks about in detail how we take these architecture into take this architecture and in practice that we add a head on top of a body. So that's a separate video just in case if you are interested. So in now this line I am just building that body, which is my BERT model. So self.BERT. checkpoint, and my checkpoint is this BERT base uncased. And now so that's my body, and now I'm going to add the head, starting with a dropout layer. Probability of 0.3. And finally, after the dropout layer, the final layer is a fully connected nn.linear. To that I need to pass the input features, which is self.BERT.config.hidden size, which is the last layer of the base model, and my out features is the number of classes. Okay, and now just a forward method. So that will output a pooled output, and let's start with it. Input IDs. So output first will start with a dropout layer, so self.drop. And my final output is just return self.output. That's it. Okay, I'm not done with the modeling file, I guess. Yes. And now coming back to the Jupyter notebook, here that's how I define my model, which is a sentiment classifier, which we just defined here. All right, and to that I pass a number of classes. Sorry, the length of the number of classes, because that's what we need. Remember these class names we have defined at the very top, which we have 5 classes. That is *1, *2, *3, *4, etc. And model, you pass it to the device. And here in these 3 lines, I'm just doing a cross check or quick check that it is actually working. And that's how I define my input IDs and attention mask, and taking from the data, pass both of them to device, and then pass these input IDs and attention mask to the model, and then apply F is coming from PyTorch, f.softmax to the entire output of the model across dimension of 1. And again, this f is just the torch.nn.functional. So coming back here, so yeah, these three lines is just for sanity checking. They're not really part of the model. And now the actual training. But before starting the training loop, I have to define a few things. First, I want to run it for 10 epochs. Then my optimizer is Adam W. To that, I pass model.parameters, and learning rate is 1e minus 5. I'm taking pretty low learning rate. And total steps, this is the length of the train data loader multiplied by epochs. So that's my total steps. And also you need to define a scheduler. And for a scheduler here, I'm making use of this get linear schedule with warmup. We have already imported it at the very top, right? Yeah, from Transformer. Okay, so this get linear schedule with warmup will take an optimizer. We'll take the number of warm-up steps and also number of training steps. So you can define a number of warm-up steps to whatever you like, but here in this case, just for the sake of simplicity, I kept it at 0. Number of training steps, that's my total steps. And loss function, because it's a multi-class classification function, normally cross entropy loss is the most often used one. And again, you need to pass that to device. Okay, so now I am ready to run my training loop, but before running the epoch by epoch, I need to define two methods for my training model and also for evaluating the model. So let's go to train.py. Model.train. These are pretty standard code for PyTorch epoch by epoch running training. So no rocket science here, or not much of new things here. So here I'm just defining a losses which will hold the losses for each epoch. So let's define it to be an empty list. Also correct predictions. So I need to start looping over data loader, right? For D in data loader. We already saw that we can access input IDs, attention mask, and targets from the data loader. So that's what I'm doing here. With the model, you pass your input IDs and attention mask. And from the outputs, you apply your torch.max to get the maximum probability, which will give you your predictions across dim of 1. Loss function is coming from arguments, and that would be outputs and targets. And now I'm going to apply gradient clipping to my model.parameters. Gradient clip grad norm. I think there's the underscore here. Model dot So quick words on this gradient clipping, that why we need that is because PyTorch saves the gradients in the parameters, and there's a chance of what we call gradient explosion or vanishing gradient. These are the two main problems you face with very deep neural network. So why do we need gradient clipping is because in a single word we tackle these problems of exploding gradients or vanishing gradient with gradient clipping. So gradient clipping, what it does is it's a method where the error derivative is changed or clipped to a threshold during backward propagation through the network. And by rescaling the error derivatives, the updates to the weights will also be rescaled, dramatically decreasing the likelihood of an overflow or underflow. And gradient clipping is implemented in two variants. One is clipping by value and another one is clipping by norm. The idea behind clipping by value is simple. We define a minimum clip value and a maximum clip value. If a gradient exceeds some threshold value, we clip the gradients back to the threshold. If the gradient is less than the lower limit, then we clip that too to the lower limit of the threshold. And then coming to the clipping by norm, the idea here is similar to the one that is similar to the one by clipping by value. The difference is that we clip the gradients by multiplying the unit vector of gradients with a threshold. And that threshold is a hyperparameter that the developer is supposed to decide during the model development. So overall, gradient clipping helps gradient descent to have a reasonable behavior even if the loss landscape of the model is irregular. All right, now I just need to do the optimization and the scheduler. This single step method will take care of both of these. And lastly, I need to make everything zero grad. So from this method, I'm returning the accuracy and the mean losses. And what is my accuracy? Correct prediction divided by the number of examples. And the mean losses is just np.mean. Okay, that's my train model. I have to define another method for the evaluation of the model, and only difference is during the evaluation there is no need to do optimization or scheduling. So let's see. It is going to be just a similar method, only much more simpler. I can copy this part here. Actually, I can copy up to this. Okay. Targets here. Even I can copy outputs and predictions. Losses, yeah, losses also I can copy. Correct predictions, losses.append, and yeah, backward is not needed for evaluation. So let's copy up to this. Okay. So now from this method, just return and okay, so both of these is made. And I also need a final method here in the training, which is for model evaluation. That is after the training is completed and I have a completely fine-tuned and trained model, then I need to test the model on the test data set, and that's another method. And that also I can copy quite a bit from here. Actually, that model, the mechanism and the steps will almost be similar. Only in this model, I start with the context manager of torch.nograd. The attention mask and the targets will just be the same. Even outputs prediction will be the same. I need to define the input IDs as well here. Yep. Now what I need? Probs, spreads are here. So I need the probabilities. So I need probs. And sorry, this is text. Okay. And similarly, finally, predictions. Prediction probabilities, also torch.stack. Real values. All these things, review text, predictions, prediction probabilities, and real values. Cool. Okay, with that, my trainer, all the methods, the 3 methods that I needed are all done. I can start my training loop. So let's go back to my Jupyter notebook. Let's print it. So one of so first I'm going to execute the train model, which will give me the train accuracy and the train loss. And also lastly, the length of df train. Oops. Similarly, I need I need to apply the eval model to get my validation accuracy and validation loss. That's it. And now just update these history, the history, with the train accuracy, train loss, and validation accuracy, validation loss. And this I'm doing each epoch. And later for any plotting, you can get those values from the history variable. Also, I need to take care of another thing, that if the val best accuracy, in that case, save the model. Best. All right, so with that, all the training will run for whatever the number of epochs you have already mentioned. And after the model is trained, now time to do model evaluation. That means I need to apply the trained model on the test data set. And also here I am just plotting a confusion matrix. So here this little method, show confusion matrix, is just for plotting a confusion matrix. It takes just one single argument, which is a confusion matrix between my prediction and the true levels. So first what I'm doing is let's zoom in here. So I am just applying this get prediction method that we just wrote here in trainer.py file for doing the evaluation. That I'm applying to that, I'm passing model and the test data loader, and what it will give me is y review text and y prediction, y PRED probabilities, and actual y test. And then my confusion matrix will just be simply to the confusion matrix method, you pass y test, that is, which is the actual value of y test from the test data set, and the y prediction, which is a predicted value after applying get prediction. And that will give you a confusion matrix, and making a data frame from the confusion matrix and passing that DFCM, that is a data frame of the confusion matrix, to the show confusion matrix method to plot my confusion matrix right here. And the last thing I want to check my model on is that how my model predicts an actual review by a genuine customer. So here, the review text, I have a review from a genuine customer. I mean, it's a dummy customer, of course. And the review text the customer writes is, I could share photos seamlessly with this app. Now, the job of the model is it takes this text or review text and predicts what is the class of star that this review text actually transpires to. That is, we have 1 star, 2 star, 3 star, 4 star, 5 star. So the model should predict the correct class of the star. So first thing, you have to tokenize this text. That's what I'm doing in the next line. Tokenizer.encode plus. I'm passing the review text and also all the other parameters. These are all standard ones that we have already used. Max length equal to max length, which in our case is 512 at special tokens equal to true. Anyway, so from these encoded review, which is a tokenized form of the text, you get the input IDs and also the attention mask, because you need these input IDs and attention mask to pass into your model, your pre-trained, fine-tuned model, to get the prediction from the model. So this line is doing just that. So to the model, I'm passing input IDs and attention mask. That model it gives output. On that output, I'm applying torch.max to get my most probable class, which is this prediction. And then all you do is your actual class is class names, and to that you pass the prediction. This prediction is actually a value from the model output. And when I do that, the output that I get from the model is 5 star. It's kind of obvious. this review text, I could share photos seamlessly with this app. This transpires to a actual review of the customer of 5-star. Now let's to this same text just add another phrase in the next example. So here all I'm doing to the actual statement, I'm adding this part, but the UI could be better. So the whole review text is I could share photos seamlessly with this app, but the UI could be better. And now the next steps are exactly the same like the previous step. And let's now see the output from the model. And now it is 3-star because obviously the customer is not completely happy when the UI could be better. So that's how the model is working. So to sum up, what we did in this exercise is we took Yelp review text from a Kaggle dataset where customers gave reviews, and also the corresponding star rating the customer gave, like 1, 2, 3, 4, 5 star. And we fine-tuned a BERT-based uncased model on that dataset by adding a classification head on top of a model body, and we got our model fine-tuned with PyTorch. And now the model is predicting, given any review text a model is predicting, and the corresponding star rating, the review text will be applicable. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So see you in the next one. Thank you very much for watching. Hey everyone, in this exercise I will train a Zero Shot Multilingual Sentiment Classifier, and the model I will use for this is Multilingual Universal Sentence Encoder, or also known as Muse, for feature generation. So this particular model and the paper was published in 2019 and specifically deals with multilingual or cross-lingual situations. So quick points about this Muse model. So the model is a dual encoder model. One side encodes a query, for example, the question in a question answer task, and the other side encodes all possible candidates, for example, all possible responses to a question answer task. The model then computes a similarity metric between the query encoding and the response encoding. The output of the model is the response most similar to the query. And two architectures were tried as the encoder. One is a regular CNN, or convolutional neural network, for parameter efficient networks, and the other one is Transormer encoder, but that requires much higher level of resources, computing resources I mean. And here is the original paper, Multilingual Universal Sentence Encoder for Semantic Retrieval. If you are interested, you can just search for it. I will give a link of this paper in the description of the video. Alright, so coming back to our exercise here, the goal is to illustrate the zero-shot classification abilities of multilingual models, where the model is only trained on English dataset and then used to predict non-English data with no further training. And for this exercise, I will use the super popular Yelp polarity dataset, which is a binary sentiment classification dataset with 0 and 1 as the target values. So the dataset will be pulled from HuggingFace Hub. This is the one that I'm talking about. The dataset consists of 560,000 highly polar Yelp reviews for training and 38,000 reviews for testing. So just as usual, this is split between train and test in HuggingFace. So to give the background, the original Yelp reviews take numerical scores from 1 to 5 stars. This dataset is constructed by grouping the 1 and 2 stars reviews into the negative sentiment class and 3 and 4 reviews into the positive sentiment class. So I will do the fine-tuning of the Muse model on this dataset. And again, talking about the Muse model, Muse is a transformer encoding text such that text of two different languages with similar meaning will result in a similar encoding. This is analogous to the way two words with similar meaning and usage will have similar word embeddings. And Muse supports 16 languages. It was trained on Arabic, Chinese simplified, Chinese traditional, English, French, German, Italian, Japanese, Korean, Dutch, Polish, Portuguese, Spanish, Thai, Turkish, and Russian. And here I will use TensorFlow Hub to load the Muse model, and the dataset obviously will be pulled from HuggingFace. And for the actual modeling code, I will be using PyTorch Lightning. So coming back to my VS Code, first you need to install your relevant packages, TensorFlow Hub, TensorFlow Text, PyTorch Lightning, datasets, and then import all those standard modules from all these packages. So I'm importing Torch, data loader from Torch, and then from datasets I'm loading load dataset, load metric, etc. Anyway, and about the overall project structure, this is the main notebook where I will be running most of the codes and also see the output. But there are two more Python file. The data loading Python file will have the job of loading all the data sets and doing the basic pre-processing on the dataset, and modeling is where I will be handling the actual building of the model with PyTorch Lightning. And that is the reason you see in this cell here that I'm importing both those files as a module, so that I can use all their classes and methods defined in those two files. And here I am just doing pl.seed everything, so that the results are reproducible. And yeah, so pull these universal sentence encoder large from TF Hub. And this is a link to where I'll be pulling this model from TF Hub. So let's quickly go through the overview. The universal sentence encoder encodes text into high-dimensional vectors that can be used for text classification, semantic similarity, clustering, and other natural language tasks. The model is trained and optimized for greater than word length text such as sentences, phrases, or short paragraphs. It is trained on a variety of data sources and a variety of tasks with the aim of dynamically accommodating a wide variety of natural language understanding tasks. The input is variable length English text, and the output is a 512 dimensional vector. All right, the universal sentence encoder large model is trained with Transformer encoder. And to learn more about TensorFlow embeddings, okay, so that's all we need to know. And so I am pulling that model in here in the data loading Python file. You just pass your model URL and then you do hub.load model URL. That's all. With these two lines, the entire model will be loaded. And the size of the model is 523 MB, so it's pretty moderate. So let's define some methods to load my models and deal with the vectors. So I will have two utils method here and one class. So first util is this method will just take a list of text and produce a NumPy array of vectors, and the vector is coming after encoding the text. It's a list of string, and it will give me numpy.nd array. Return and specifically I'm returning a NumPy list from here, or NumPy array from here, because I want the vectors to be handled by PyTorch. I just don't want to remain as a TensorFlow tensor, because the whole project will be built with PyTorch Lightning. Okay, and then I need another method. This encoder factory method will take a dict of string and integer which is labeled to integer mapping, and then return me a batch by batch data of batch embeddings and batch label. Let's write it, and then it will be clear. This is going to be a dict of str. Sorry, it's batch embeddings. Embed text. Label to int. Syntax mismatch here. Okay, so these are my two util methods, and now I'm going to define a class, the job of which is to get the data, prepare the data, and set up the original pool data for feeding into the PyTorch Lightning model. Yelp data loader. That's going to inherit from PyTorch Lightning data module. Batch size. And now I just need to define now I need to do prepare data. And this method the job here will be to load only partial subset of the original data from the Yelp polarity review, because otherwise the training will it will load. Let me see, 1 second. So in the original data of Yelp polarity, there is no validation set, only train and test. So what I'm going to do here is during the loading itself, I am going to take only partial part of the data for my test and train and also validation. So I need to split it right during the loading. So load dataset Yelp. This is where I'm going to split test 2 percentages here. Next will be 2%, and so this is my test, sorry, and this will be my train and val. Yeah. So what this will do is it uses the first 2% of the train and test sets to train and test respectively, and it uses the last 1% of the training set for validation. And so last 1% of the training set. So this will be train. Yeah. So this is where I'm going to define my label to int. That means I have to enumerate over the label names. Yeah. So on the setup, first I'm going to compute embeddings in batches so that they fit in the GPU's RAM. And here I'm going to use the map function of HuggingFace. I need to set the format to PyTorch tensor because we are going to use PyTorch Lightning here. Columns are Valdias. Oh, I forgot another argument to set format, which is output of all columns to true. Output all columns here. That is defaults to false. Keep unformatted columns as well in the output as Python objects. Okay, yeah. Okay. Oops. Why so many things are coming? Again, I don't know. And it will take batch size. Okay, and I need to repeat this for building my val data loader and also test data loader. There they are. Okay, so I'm done with data loading. So now back in my Jupyter notebook, I can use that Yelp data loader, that method that we just, that class that we just built here. And that's how I get my data. One that is pulling from the Yelp polarity review dataset, and also I prepare my data. And what is prepare data? That's this method that we wrote inside our Yelp data loader class. It will just create this label to int and the encoder, etc. And now here I'm just checking the length of this train validation and set train validation and test, and they are my length of the data. Okay, so now I need to start the actual model building. So the multilingual binary classifier, that's target here, and also it's a zero shot learning because I'm going to apply the same learning on other languages to do the translation by the model. So Lightning module organizes your PyTorch code in 6 sections: computations, train loop, validation loop, test loop, prediction loop, and optimizers, and learning rate schedulers. And that's a kind of architecture that I'm going to build. But I need a model class which will incorporate all these different section or all these different architectures within the same class, and that I'm going to write inside my modeling Python file, this one, and then bring in that model class by just doing this. So let's go to my modeling file. This class as well is going to be inheriting from PyTorch Lightning module. So okay, so all these are self train accuracy, val accuracy, test accuracy, hidden dim, dropout probability. Yeah. Now learning rate, you can actually reduce it even further, maybe. Because we already saw that's the maximum sequence length acceptable by this model that we are using from TensorFlow Hub. It was clearly written in their documentation. So that's all. I'm setting it at 512. So now I'm building these layers by appending one after another layer on top of each other. And for example, here, based on these conditional dropout probability, I'm adding the dropout layer to the layers. So here. And also note here the very important point that I always mention in all other previous fine-tuning videos as well, that here we are following the same architecture, which is that I'm adding a head to a body. So the body is the base model, and on top of that I am adding this classifier linear layer, which is a head. So that's how my whole model will be built. And that is what is fine-tuning all about. Okay, now I'm going to add some linear layer. Linear, to that I add And what was hidden dims? That's this 768 by 128. So this nn.linear takes the first two arguments as in features and out features. And now that I have given prevdim and h as my in features and out features for the before the next layer, I need to update my previous dim to be the out features. So let's, because I'm going to use these prevdim for the next linear layer. You'll see that in a second. Now again, checking for dropout prob. Yeah. And after the ReLU, come out of that for loop, and here the last linear layer. And 2 because it's a binary classification problem, so our number of classes is 2. Self dot. Okay, now the next method is forward. So here X will be a batch of USEM vectors. USEM is our model. Logits. Diff now configure optimizer. Oops, again unnecessarily it's taking everything. This auto intelligence sometimes is really problematic. Yeah. My optimizer is dot Adam W. So, sorry, just the Adam. Self dot learning weight. Okay. I need the loss function. Which will be readings. Predictions will be from on the logits. I need to get the maximum from the logits across a dimension of 1. So torch dot arg cross entropy, logits and y. Return the loss, reds, and y. First, I need to get the output from the compute loss. I can do add batch here because this train accuracy is this one, a load metric accuracy. So we can do add batch on this, and also after that we have to do compute. So add batch, that will take and the next one is reference. Self dot second. Now this is another beautiful feature of PyTorch Lightning, this log dict method, where I can tell the model that during the training to save quite a few things on after each epoch. So this is where I define that the log dict should automatically accumulate and logs at the end of each epoch. Progress bar. I'm going to copy the same structure for both my validation and test step. So here it will be I did not return anything from that function, so I need to return loss. And this also, test accuracy. Yeah, I think that's it. All right, now I come back to the Jupyter Notebook, and here So now I can do modeling.model, and that's how I define my model. And then before actually training, I need to start defining a couple of configuration into the checkpoint. Lightning dot, sorry, yes. For file name, that's the way that the model will be saved. That's it. You also need to define the trainer class, pretty important. Lightning.trainer. And definitely I suggest you go and check their official documentation. There's a beautiful, many guidelines are written in their documentation. So here, first argument, I need to specify the number of GPU. So I'll be running it in Colab or Kaggle. That's obviously 1. And now finally the training loop with you just pass training.fit, pass the model data.train data loader on which the training will happen, and also the validation data loader on which the loss will be calculated, and that will be monitored. That is because I have mentioned the monitor is val loss, so the loss on validation dataset will be monitored. And under the hood, the Lightning trainer class handles the training loop details for you, so you don't have to worry too much. It's much easier compared to regular PyTorch. So it automatically enable or disable the gradients. It runs the training, validation and test data loaders, and also call the callbacks at the appropriate times, and also it puts the batches and computations on the correct devices. So everything is pretty much taken care of for you by PyTorch Lightning. All right, after running for 15 epochs, this is what I got, that it stopped because maximum epoch of 15 reached. So now I need to validate and test a model. So during and after training, we need a way to evaluate our models to make sure that they are not overfitting while training and generalize well on unseen or real world data. And there are generally 2 stages of evaluation: validation and testing. To some degree, they serve the same purpose to make sure models work on real data, but they have some practical differences. Validation is usually done during training, traditionally after each training epoch. It can be used for hyperparameter optimization or tracking model performance during the training. It's a part of the training process itself. But testing is usually done once we are satisfied with the training and only with the best model selected from the validation metrics. So now that this training and validation metric part is over in the previous cell, now the testing part. And with PyTorch training, you do this trainer.test and you pass your test data loader to the data loaders, and that will produce your very important metric, which is your test accuracy and test loss. So I got my test accuracy at 0.89 and test loss is 0.25. And now finally the inference time. So you get your best model from your model, and this is our model class which was defined in the modeling Python file here. So from your model, you just apply load from checkpoint, and from the checkpoint callbacks, you load your best model path. and that will really load your best model. And this best model now will be needed to do our next step, which is inferencing. Now for this one, for inferencing, I definitely need to define and write another little util function which will do the prediction. But before, note this particular thing, that since we use this model use embeddings, which is a cross-lingual model or multilingual model, so we should be able to predict sentiment for non-English languages as well, because this USEM model was trained on 16 languages, all the 16 languages: Arabic, Chinese simplified, Chinese traditional, English, French, etc. And that's what now we are going to do. So the method that I'm going to write now is going to take as input a list of text, which are input text, and the job is to predict the emotion on those text. So this method will convert the text to an embeddings, then pass or feed those embeddings to the best model, and then from the model it will get back its output, and finally the method will return the original text, the predicted label, and also the predicted score. It will take a list of strings. So I just converted the text, got the embeddings from the text. Cross the dimension of 1. The results will be a dict the value pair. First the original text, and I'll just return the result. Now the most interesting part, just apply these predict method on to predict some example text. So this first English text, I took it from a test set from my data set, which is this ELP polarity. I just from the test portion of the data set, I just randomly took a positive sentiment review by a customer. And so what this is, like any Barnes and Noble, it has a nice comfy cafe and a large selection of books. The staff is very friendly and helpful, etc. And then with the Google Translate, I translated that to German. Because I'm going to pass both these original English and the German to my predict method here as a list of text. And look at this, the prediction from the model is level positive, score 0.998, pretty high, and also the same positive level for the German part, and score is also high, but not as high as the English, but still very, very high. So that's the magic of multilingual or cross-lingual model building. Now I'm going to do another thing, another example here. I'm going to pass English text, then converted the English text to Italian using Google Translate, and also to Finnish with the Google Translate again. So all of these three texts I pass to the model, and now this time the review is negative. So the text is the inside of the restaurant was not clean at all, and we also did not like their lighting arrangement, too dark. Okay, but here just note another important and interesting part. This Finnish translation, Finnish was not part of the original 16 languages on which this USEM model was trained, but I still wanted to check whether the model can somehow work on the Finnish. So I do again, I just to the predict method, I pass all this English, Italian and Finnish, and let's see the prediction. So for all of them, it very correctly predicted negative. For the English, negative score is this. For the Italian, negative score is this. And even very interestingly, for the Finnish translation, it gave me a negative level. The score is also pretty high. Now, obviously, these first two prediction were expected because the model was trained on both the Italian and English language. It's a multilingual model, but we do not have, or I do not have, a very good explanation how this model also worked on Finnish, and some possible reason could be thought of. So one possible explanation is that during the training of USEM, they used a technique called subword units, and so in this case, the USEM's model's tokenization lets the transformer learn which subword units are used across languages. So I can only imagine that the subword unit used in Finnish language are close enough to those in the other 16 languages that the USEM model was trained on. But I have to say that I was actually experimenting quite a bit with few other customer reviews as well. So for this particular review, this Finnish language also has produced a correct labeling, but for few other more confusing kind of customer reviews, this Finnish language translation or the prediction did not work as well. For example, for Italian and English, the model predicted very correctly whether it was negative or positive sentiment, but for the Finnish, when the original review is a little bit confusing, the model could not understand it. So yeah, so that's kind of interesting, but the main point is that the multilingual model USEM worked pretty well for the languages that they were trained on and they were supposed to work. Yeah. So to summarize, what we did in the exercise is we trained a Zero Shot Multilingual Sentiment Classifier using this USEM model on our ELP polarity dataset and got our prediction, and that is looking to be working very correctly. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So see you in the next one. Thank you very much for watching. Hey everyone, how's it going? So this video is about zero shot learning, where I'll be training XLM-Roberta on German corpus and then applying that trained model to predict on French, Italian, English, and I think another language. So the basic idea of zero shot
transfer learning is that you train on one data set, then transfer that learning to another data set to do your prediction. And this video is going to be slightly longer, so brace for a long journey. Let's start.
So what is this XLM-Roberta model? The Facebook AI team released XLM-Roberta in November 2009 as an update to their original XLM100 model. Both are transformer-based language model, that is both XLM-Roberta and XLM100, and both rely on the masked language model objective, and both are capable of processing text from 100 separate languages. The biggest update that XLM-Roberta offers over the original is a significantly increased amount of training data. The cleaned common crawl data that it is trained on takes up to a whopping 2.5 terabyte of storage for the case of XLM-Roberta. So it is several orders of magnitude larger than the Wiki 100 corpus that was used to train the original XLM100. And this Roberta part comes from the fact that its training runtime is the same as the monolingual Roberta model, specifically that the sole training objective is the masked language model. There is no next sentence prediction like BERT or sentence order prediction like Albert in XLM-Roberta. Okay, so initially all my regular imports over here, nothing very special. I'm just importing all the standard modules and packages, transformer, then some of the model, token classifier output, Roberta model, Roberta pre-trained model, then auto config, auto tokenizer, and I'm also going to be using these ACQ EVAL sec eval package for my calculating the various matrices during my training. And now the dataset for this video that I'm going to use is called Extreme. That's a very popular and very well-known dataset, and it's really large. You can see that the total amount of disk used is that's 1.6 terabyte. Yeah, so we have to work with various subset of this dataset, and we can check all these subsets right here. There are so many of them, and this is this site also is the homepage of the Extreme dataset in HuggingFace. And again, here we can see under these drop down the various subset of it, and this is GitHub pages of Extreme dataset. So about the Extreme dataset, it's a multitask benchmark for evaluating cross-lingual generalization. The languages in Extreme are selected to maximize language diversity. What we can see here, these panx, he, .fr, .fi, all these last two letters, that's actually are denoting the corresponding languages, that is for the various subset. And for this video, I'm going to use the span X subset. This is the most well-known in among all the subsets under Extreme. So let's go to my VS Code. And here I'm going to load that dataset from Hugging Face Hub. And to load one of the PanX subsets in Extreme, we will need to know which dataset configuration to pass to the load dataset function. And whenever you are dealing with a dataset that has multiple domains, you can use a particular function named get dataset config names that comes from the datasets module of Hugging Face. So let's start typing the code, and then it will be much more clearer. Get dataset config names, that's the one I'm going to use. Extreme. And I'm going to print let's print Extreme has len That's my extreme subsets. Yep. Let's print it and see what I get. Get dataset config names is not defined. Why I'm getting that? Let me quickly figure this out. Oops, sorry. That's because I never ran these this cell, which has this has all the imports. So I need to first run it, and then module not found. Which one? Sec eval. All right. So I need to install it. So just do yeah. So I just installed sec eval, and now I'm just going to print these lane of extreme subsets. Let's run this cell. Yeah, so I have 183 configurations, and let's print them out. Panx sets starts with, that would be cat. Yeah, so that's all the pan X subset within extreme. And we can see that the last two letters here that represent the actual languages that they represent. So I have .en for English, .de that's for German language, and I think .bn is for Bengali, .fr is for France, French language. All right. So let's and so this means that to load the German corpus, we need to pass DE, that is this one. Where did it go? Yeah, the DE as part of the name. So that's what I'm going to do. Load data set. Yep. Awesome. So that's my dataset, and it's coming from HuggingFace dataset module, and that's why I have this special structure, which is dataset dict. Under this dataset dict, I have three splits. That is train splits, under which I have 20,000, validation number of rows 10,000, and test number of rows 10,000. Cool. So to make it a realistic, now what I'm going to do, I have to make a corpus of European languages, and for that, for making a realistic European corpus, what I'm going to do is to sample the German, French, and Italian and English corpora from the PanX according to their spoken proportions. And this will create a language imbalance that is very common in the real world dataset. So definitely to represent the real world, my datasets, the different parts, that is the English, French parts, will not be equally distributed. Their proportion will represent the proportion that they are actually distributed in the real world. And so keep track of each language. Let's create a Python default dict that stores the language code as the key, and a pan-x corpus of type dataset dict as the value. And what is default dict? The Python default dict type behaves almost exactly like a regular Python dictionary, but if you try to access or modify a missing key, then default dict will automatically create the key and generate a default value for it. This makes a default dict a valuable option for handling missing keys in dictionaries. So that's pretty much the main difference between a Python default dict and a Python dictionary. So now my languages will be a list of DE for German language, FR, Italian, and English. And for the percentage spoken, I have taken particular percentages from regular Google search. That is to what percentage of European people speak German, things like that. It's not going to be very perfect. I have not spent a huge amount of time to get the perfect data. It's more or less like a ballpark. So percentage lang. So my percentage will be, that's my percentage, then x ds combined. That variable will be a default date. And that's also will be coming from dataset dict. Cool. And now I need to make sure that this span x ds combined, this variable contains all these four individual data sets within this variable as a dataset dict. So we have already seen from this line that is a single dataset. For example, here the German.d dataset contain these dataset dict, and now I need to just get these similar for the other three, that is the French one, Italian, and the English one, and combine them together inside the span x ds combined variable. So let's do that with the for loop. Oh, sorry, for lang and percentage. I'm going to zip languages and also percentage lang spoken. Now I need to load each individual dataset. So ds will be extreme and x. With that, I have to attach the language. All right, that should work. And also I need to shuffle and downsample each train test validation according to the spoken proportion. So for train test val in ds, remember this ds will have these splits already within it. I will have a train, I will have a validation, and I will have a test. So that's what I'm doing for train test val in ds. And x ds combined lang test val. This will be the corresponding split. It may be train, it may, then the next one will be test, and the third one will be val validation. That will be equal to let's shuffle it. And this shuffle method is coming from HuggingFace datasets module. Also select, and what I'm going to select, only these percentages. So that's where I'm going to use we have already zipped these language and percentage lang spoken. So each of my percentage will have each of these value. So dot select range integer, then percentage ds and test val dot number of rows. So I'm just multiplying the percentage with the entire split and then doing dot num rows, and that should work. Now let's do pan x ds combined. So let's run this cell. And after running this cell, now run check the result. Cool, looks like it worked. Yeah, so I have this dataset dict, and within each dataset dict I have a dictionary, and each of these dictionary contain each of the language. So the first one is German, that is DE. Under DE I have another dataset dict, which is inner data dict. Then the next one is French, that is also a data dict. And similarly I have for this if I open this size limit I'm getting here. So let's open this in a text editor. Yeah, now it's looking right. Yeah, so the first one is German or DE, next one is French, third one is Italian, and the fourth one is English, and each is split into train, validation, and test. Cool. And another quick note here on the use of shuffle. So I mainly use this shuffle so that to make sure that we don't accidentally bias our dataset splits. So the shuffle function randomly rearranges the column values. You can specify the generator parameter in this function to use a different random.generator method if you want more control over the algorithm used to shuffle the dataset. And also I use this select. This returns the rows according to a list of indices, and here my list of indices is just this integer, that is percentage multiplied by the whole split num rows, and that's converted into int, and that's the whole range I'm taking. All right, now let's move on. Okay, cool. Now let's see how many examples we have per language in the training sets by accessing the dataset.numRows attribute. Okay, I think I have already imported pandas here. So I can directly do pd dot. Why I'm getting pd? Okay, let's just import it again. So here, what I'm going to see, the various language name will be my column names. So lang, then ds combined. That would, I would take the lang, and I'm only interested in checking the train dot num rows for lang in languages. Let's just print it. Yeah, so I have 12,580 Deutsche or German training sets, for French 4580, and so on. Cool. Now we have so what do you see, that we have more examples in German, as the percentage for the German was highest than all other languages combined. So we will use it as a starting point from which to perform a zero-shot cross-lingual transfer to French, Italian, and English. That is, I'm going to the next part of my work first will be to fine-tune XLM-Roberta on this German dataset, that is the German corpus, and then transfer that or do the zero-shot learning, cross-lingual learning on the French, Italian, and English dataset. And if you are wondering what is zero-shot learning, in simple words, whenever we train a model without giving it the desired input, that is called zero-shot learning. For example, task of recognizing an object but not passing the relevant images for it, that's an example of zero-shot learning. And in this case, when I'm going to fine-tune my training on these German dataset and use that model to predict a prediction on French, Italian, and English, that's an example of zero-shot learning, because I'm not training the model on the French, but I'm using the model on the French dataset. And that's the core principle of zero shot learning. And that is, I do not have the relevant input data set, but I'm still going to use the same model on that different data set. Okay, so now let's move ahead. Now let's just quickly inspect one of the examples of the German data set. So DE and train. Let's just take the first element and let's print the key and values. Dot items print f e and value. All right, so this is my single element key and values. And the keys here correspond to the column names of an arrow table. And what is an arrow table? That's a different topic altogether. But basically just know that these HuggingFace data dict is arranged following the arrow table format or arrow table data structure and data architecture principles. So anyway, here the keys correspond to the column names of an arrow table, while the values denote the entries in each column. So in particular, we see that these NER tags column correspond to the mapping of each entity to a class ID. So these numbers are actually class IDs, and each number in this class ID for NER tags represent an entity. We can convert the number to a label name for more information if we want. And these class IDs are not understandable just by looking, that is, by the human eyes, it is not understandable. So let's create a new column with the familiar NER tags, that is LOC, PER, ORG tags, that is location, person, or organization tags. And to do that, the first thing to notice is that our dataset object has a feature attribute that specifies the underlying data types associated with each column. Okay, so we can actually check that pan x dx combined de train. Yeah, so features is token NER tags and langs. This is exactly what we saw here with the corresponding values as well. Yeah, so now what I'm going to do is to use this features.items method so that I can actually check the underlying data types associated with each columns. So here previously I just printed these key values in element.items, but now I'm going to use feature.items. One second, for key value in panxdx combined, sorry, de features dot items. Key and value. Let's put. Yeah. Now when I run this cell, I get this output, and now I can actually see the underlying data types, and that's what features.item do. That is, my tokens are of sequence type, NER tags that is also sequence, and langs are sequence as well. So basically the sequence class in HuggingFace specifies that the field contains a list of features, which in this case, which in the case of NER tags correspond to a list of class label features. And we already saw that when we printed it here. That is, NER tags is this sequence, langs is this sequence. Now let's pick out the these NER tags feature. NER, that was tags. All right, so these are my class names for the NER tags, and I have 7 total number of classes. Okay, now let's convert these NER tag class names integer, that is these integers, to strings, class name strings. For that, I'm going to define a quick function. Return, that will be str, and the values will be tags dot into str idx for idx in batch NER tags. Now to apply this function, I'm going to use the map method. Dot map, and then just pass this create tag names function. Yeah. And now it's just extracting the into steer. All right, so this is my panxd. So basically this into steer method converts an integer to class name string. In here, it will create a new column named NER tags str in our training set with class names for each tag. And we can see that this new column has been created in the features. And the map method returns a dict with key corresponding to the new column name and the value as a list of class names. Let's check panx de train data element. Output, okay, and let's open it in a. Yeah, so I have these tokens, NER tags, langs, and the new column names, NER tags str. Okay, and now let's get a data frame based on this particular panx de. So de panx de train 0. Sample tokens. You already saw that we have a tokens feature or tokens key. Okay. The example, and then let's take NER tags str and sorry, name of those, sorry, tokens. I have to put a T. Tokens and tags. Cool. So these are my tokens and these are my tags. And now, as a quick check that we do not have any unusual imbalance in the tags, let's calculate the frequencies of each entity across each split. And for that, I need to define a quick util function. And also by entity, I mean these NER entities, named entity recognition entities, that is LOC, PER, person, or organization, ORG. Let's first check this variable pan x de dot items. Okay, so we can see that it's a list, and within the list I have a train split, a validation split, and a test split. So what I'm going to do, I'm going to count the number of these NER tag string, that is these LOC, PER, etc. under each of these split, that is under each of train, validation, and test. So let's I think I have already imported the counter earlier. So let's define a function get NER frequencies pan x de. Now I'm going to use the default dict again. Split to frequencies is a variable which is a default dict of counter. And remember, this counter is coming from the collections module. That is at the very top, I have imported a line named as from collections import counter. Now I have to start looping for through the span x de dot items. So for split data sets span x de dot items for row in dataset NER tags str, because that's the list items through which I'll be looping through. That is these NER tags will contain all these NERs string. So for row in dataset NER tags str, for tag in row, if tag dot starts with b starts, yeah, because I'm counting the beginning tags starts with b, then I have to split by the hyphen. So my tag type will be equal to that's my delimiter for splitting, and then taking the first element after splitting, and then update split to frequencies split. This split is actually train, test, or validation. Tag type plus equal to 1. And finally, just return the split to frequencies. Let's check if it is giving the expected results. For UQUENCIS equal to get NER frequencies. To that, I pass pan x de. Okay, and print these frequencies. Yeah, looks like this is exactly the way that I wanted. So it's a default dict, and the internal elements are all collections.counter. And I have train, validation, and test. Within the train, I have a counter for LOC, ORG, and PER. Validation, I have the similar counter for ORG, LOC, PER. Again, for test, I have LOC, PER, ORG. Okay, now all I need to do is to print it in a data frame format. Data frame from dict, because that's a dictionary from dict, and then I pass frequencies and orient equal to index. Cool. So that's my that's a distribution of the various NER tags in my dataset. And this looks good because the distribution of the PER, LOC, and ORG frequencies are roughly the same for each split. So the validation and test set should provide a good measure of our NER tagger's ability to generalize. All right, with that, let's now start doing our actual multilingual transformer modeling. And for that, first thing to do is to build a custom model for token classification. And we already have imported the required libraries, which are these XLM-Roberta config, token classification, Roberta model, and Roberta pre-trained model. All these I'm going to use now. So this will be a custom class, XLM-Roberta for token classification. That's the name of our class, and that's going to be a child of Roberta retrained model. And our config class will be XLM-Roberta config. First, defining the init method. Init config. Self.num labels, which will be equal to, I'm going to get it from the config, and that would be num class, sorry, num labels. Then load the model body. Roberta model. To that I pass config dot, sorry, config dropout prob. Self.classifier will be nn.linear model. To that I need to pass the hidden size and num labels, so both are coming from config. Now load and initialize the model, and for that self.init weights. I definitely recommend you go through the documentation, and you will get the definition of all of these config.num labels. Okay, and now that's my init model ends, and next one is forward. Attention mask is also none. Token type id is equal to none. Last, no, I need the labels. set it to none as well. And the last one is quarks, double asterisk and KWARGS. All right, before proceeding further with the forward method, just one thing I forgot to mention earlier is these architecture while using Hugging Face. Very popular and very common technique, that is the differentiation between the head and body while using the transformer pre-trained models in Hugging Face. So when we switch from the pre-training task to the downstream task, we need to replace the last layer of the model with one that is suitable for the task. And this last layer is called the model head, which is this green box over here, and it's that part that is task specific. The rest of the model is called body. It includes the token embeddings and transformer layers that are task agnostic. This structure is reflected in the transformer code as well. The body of the model is implemented in a class such as BERT model or GPT-2 model that returns the hidden state of the last layer. And then the task specific models such as BERT for masked LM or BERT for sequence classification use the base model and add the necessary head on top of the hidden state. So the question you might ask is, why will I need to use the head and body separately? So some models on Hugging Face are trained on downstream tasks like question answering or text classification and contain knowledge about the data they were trained on in their weights. Sometimes, especially when our task at hand contains very little data or is domain specific, such as maybe medical or sports specific task, we can make use of other models on the hub trained on task, not necessarily the same task or as our task at hand, but falling within the same domain, such as sports or medicine in general, and thereby making use of some of the pre-trained knowledge these models already have to apply on our specific situation. So basically, what we do is that we take that already pre-trained base model and then just append a head model or the task specific model on top of that base model, and that's how these head and body terminology comes into play here. So a very simple example would be if, say, we have a small data set about classifying some financial text being positive or negative in terms of sentiment. However, we go into the hub and find that a lot of models have been trained for question answer related to financial text. In this case, we can take certain layers from these models to improve on our own sentiment analysis on financial text data. And another simple example is when a certain domain specific model has learned to classify text into 5 categories from a huge dataset it was trained on. And now I say, for example, I have a completely different dataset in the same domain, but I only want to classify the data into 2 categories instead of 5. Here again, we can use the pre-trained model's body and add our own head in an attempt to augment domain-specific knowledge on our own task. So to sum up, these separation of bodies and heads allow us to build a custom head for any task and just mount it on top of a pre-trained model. And here in this case, where I'm building this custom token classifier, I'm pretty much doing the same thing, that I'm mounting a head on top of the hidden state of a pre-trained model, which is my body. So let's move ahead building the forward method. So now use the model's body to get encoder representation. That would be self.Roberta. Token type IDs equal to IDs and keywords. Then apply classifier to encoder representation. So sequence output, that would be self.dropout, and outputs 0. Logits would be self.cla classifier sequence output. So to get the logits, I'm just applying my sequence output from the dropout layer and passing that through the classifier. That would give me the logits output. Now calculate the losses. None for here. Now if labels is not none, loss dot cross entropy loss equal to that I need to pass logits.view -1. First dimension will be inferred. Why my logits are saying not defined? logits. Okay, let's just move on for now. And self dot num labels, second dimension. Finally, return my token classifier output. Logits equal to logits. Hidden states equal to outputs dot hidden TATES. And finally, attentions equal to outputs dot attentions. Cool. It still says logits. Okay, 1 second. Let me fix that. Actually, I think this is just a Pylance thing. That logits is not defined by in Pylance. Okay, leave it. Let's just ignore it for now. Okay, now for this class token classifier output, you have already imported that, but let's quickly check out their documentation. And here I'm looking at the official documentation of token classifier output, and we can see that the parameters it takes, it's properly defined here. Loss, this is a classification loss, and it's a torch.float tensor of shape 1. Logits, classification scores before softmax. Hidden state, this is the optional true response tuple.torch float tensor, and hidden states of the model at the output of each layer, plus the optional initial embedding outputs. And attention is the attention weights after the attention softmax used to compute the weighted average in the self attention heads. Cool. And now we are ready to load our token classification model. We will need to provide some more additional information beyond the model name, including the tags that we will use to label each entity and the mapping of each tag to an ID and vice versa. All of this information can be derived from our tags variable, which as a class level object has a name attribute that we can use to derive the mapping. So let's check what is tags at this moment. So this is our tags variable. It has a name classes and names. Okay, now what I'm going to do, index to tag. that will be idx for index and tag in numer enumerate over tags.name names. Yeah. Similarly, I need tag to index, and in this case, I just need to do it tag idx for idx tags in enumerate. Okay. Let's quickly check if it's working. Index to tag. Then run this cell. Yeah. So now I have index to tag. Similarly, let's print this. Yeah. So now I have tag to index. Yeah, these two variables I need. And now define few more things here. So we will store these mappings and the tags.num classes attribute in the autoconfig object. The autoconfig class actually contains a blueprint of a model's architecture. When we load a model with automodel dot from pre-trained and then pass a model checkpoint, the configuration file associated with that model is downloaded automatically. However, if we want to modify something like the number of classes or label names, then we can load the configuration first with the parameters we would like to customize. So let's define our model names. And these names you again get from HuggingFace Model Hub. The first parameter goes is a model name. X.norm classes id to, we already have this id to, I think we already defined this index to tag. Yeah. So this is this one, index to tag this dict object, and label to IDs. That will be the opposite, which is tag to index. So now we can load the model weights as usual with a from pre-trained function with the additional config arguments. Note that we did not implement loading pre-trained weights in our custom model class. We get these for free by inheriting from Roberta pre-trained model. And where did I do that? Roberta pre-trained model inheritance. That's in our custom definition here. So here we defined all this pre-trained model that is that these our custom model is going to be inheriting from, which is this one, Roberta pre-trained model. And this one we have already imported at the very top. All right. As usual, I want to keep all the tensors in the same device. So define my device. So q dot is available. else CPU. Okay, here I am defining this final model, which is XLM model, and the first parameter is the this custom model that we defined, that is this one, XLM-Roberta for token classification. Copy this long name, paste it here from TRAINED from pre-trained, and then the inside will go XLM model name, XLMR model name, config equal to XLMR config, and pass the whole thing to device. So, and now I have to actually to train all these, I have to go to Colab because my local machine's GPU will not support this, I guess. So yeah, but let's just write few more lines and then I will move to Colab. And after the model is trained, what I'm going to do, I'll do a quick usage with some random example string. So let's define just any random example string, and then what I'm going to do, apply the train model on this. But this is after the training So XLMR. Actually, no, this is before the training. I'm just applying these model on a random sample of text. So tokens, XLMR tokens equal to XLMR tokenizer. We have defined this XLMR tokenizer here, which is auto tokenizer.from pre-trained, and then I pass a relevant model name to that. Example string dot tokens. Okay, yeah, all right, so let's run it from this line onwards. And I got a syntax error. Positional argument follows keyword argument, and that's because this one, I did not pass the keyword argument, and here the keyword is actually id to label, and that should be equal to index2 tag. Yep, now it should run fine. Yep, so it ran all well, and now I'm just going to print these XLMR tokens. Yeah, so that's my token after applying the tokenizer. And the only things to note here are these special tokens, these beginning string token and the ending string token. And these have a token IDs of 0 and 2 respectively. So okay, so finally now I need to pass the inputs to the model. So I'm going to write a util function which will take any text and also take a model and a tokenizer, and that util function will predict the tokens and the tags from that text and based on that model, and return me a data frame with the tokens and the tags. So basically, this util function that I'm going to write now, this will extract the predictions by taking the argmax to get the most likely class per token. So let's start that. This model will take text, tags, first I need to get the tokens with special characters. then encode the sequence into IDs. And for that, I need a tokenizer. So I'm going to use XLMR tokenizer. Because I need PyTorch, hence return tensor equal to PT. Input IDs and dot to if you want, you can pass a print statement here to just continue checking that your function is doing the correct thing. So input IDs are token indices. They are the numerical representation of tokens. A list of these representation is called sequences used as input by the model. And next, I want to get predictions as distribution over 7 possible classes or 7 NER tags. We have already seen we have 7 num classes. Outputs. If shape of outputs, and I want to print shape outputs. Yeah, so the outputs logits have the shape of batch size, number of tokens, and num tags. So it's something like this. Let me, yeah, so these the output logits will have a shape like this, and with each token given a logit among the 7 possible NER tags. Now take the argmax to get the most likely class per token. Which.argmax outputs across the dimension of 2. I also want to do a print statement over here. And finally, convert to a pandas data frame. So threads equal to, let's first do this thing. Tags dot names. We already have seen that our tags have names. So let's quickly check I'm doing the right thing. Yeah. So tags have this names key P for P in predictions 0, and I need to pass it to the CPU. Data frame threads. Index will be tokens and NER tags. Now I need to check that this model is working, so get NER tags. We already have an example string, pass that string tags to that, For the model, I'm going to use our named model, which is XLMR model name, and also XLMR tokenizer. Oh, because I'm using XLMR tokenizer here. Here I should not use XLMR tokenizer. I can just yeah, let's just do it like this. Okay, should work. Let's see. I made a little mistake here. That's this one, XLMR model name. So that would be actually XLMR my model. That is our custom model that we have defined earlier. Okay, with that, let's run this cell. Yeah, it ran very correctly, and this is the output that I got. So I have tokens and tags presented in a pandas data frame format, and previously all these print statement has printed, for example, the input IDs. This is my input IDs, and then shape of the output is 187. That is that represent what I put as a comment here. Batch size, num tokens, number of tags, and then prediction is another tensor. That's this. Okay, cool. Now let's move ahead and do the rest of the things. All right, now I need to tokenize text for NER, and since the XLM-Roberta tokenizer returns the input IDs for the model's inputs, we just need to augment this information with the attention mask and the label IDs that encode the information about which token is associated with each NER tags. Let's quickly look at how this works with our single German example that we saw earlier, that is the DE example sentence, by first collecting the words and tags as ordinary list. And now that I'm going to have to use the GPU, so I'm fully in Google Colab at the moment. I'm going to use DE example tokens and also NER tags. And if you have forgotten what DE example is, let's quickly take a look. What does it give me? So that's my D example. I have lang, NER tags str, and tokens within the entire dict. Cool. Now, yeah, so now with this line, I'm getting my NER tags and tokens as list. Okay, next, I have to tokenize each word and use a particular parameter in HuggingFace called isSplitIntoWords argument to tell the tokenizer that our input sequence has already been split into words. And I definitely recommend check their documentation to know what this isSplitIntoWords does. But let's quickly first write the line and then it will become clear. So tokenized input example tokens split into words equal to true. So that's my tokenized input, and my tokens will be XLM tokenizer. The code intelligence in Google Colab is kind of slow, so by the time I type it, my typing is over, then it comes. So it's not much of use, really. So XLM tokenizer, convert IDs to token. That's what I need to use. Convert, yes, IDs to tokens here. To that, I pass this tokenized input. From there, I take input IDS. Let's see if it runs. Yeah, it ran. This cell got executed correctly. Did I run this one? Yeah. Okay. So from if you go to the XLM, the tokenizer documentation in Hugging Face, it is clearly written that is split into words is set to true. When it is set to true, the tokenizer assumes the input is already split into words. For instance, by splitting it on white space, which it will tokenize. And this is useful for NER or token classification. But remember that is split into words does not mean that the text was already pre-tokenized. It just means that the string was split into words, not tokens, that is split on spaces or that kind of delimiter. And now that I have the tokens, let's see them by having a pandas data frame. Tokens index will be cool. So that's my tokens represented in a pandas data frame, and this sentence is coming from the German sentence that we initially declared, a random German sentence. And as you can see, this beginning string and ending string is coming as well, and that's expected. Okay, so in this example, we can see that the tokenizer has split the original sentence. And since we are following the convention that only underscore, take for example, this particular string. This is underscore Einhauner. I don't even know how to pronounce it very correctly. And since we are following the convention that only these underscore Einhauner should be associated with the beginning of a location label, that is B-LOC label, we need a way to mask the subword representation after the first subword. And for this purpose, tokenizer module of Hugging Face contains a method called word IDs that can help us achieve that. So let's see what actually this word IDs method do. So here I am in the official documentation of word IDs in Hugging Face, and it says that it returns a list indicating the word corresponding to each token. Special tokens added by the tokenizer are mapped to none, and other tokens are mapped to the index of their corresponding word. Several tokens will be mapped to the same word index if they are part of the same word. Yeah, so this is important. Several tokens will be mapped to the same word index if they are parts of the same word. And it returns a list mapping the tokens to their actual word in the initial sentence for a fast tokenizer. All right, let's include that. Tokenized input dot and then print just print word IDS, and also make a data frame of tokens and word IDS, where the index is equal to, as usual, tokens first. Next one is word IDS. Okay. Cool. So this list is my word IDs. That's after invoking this word IDS method. And again, what it did is that the special tokens are given none. So I can see none here and also none at the beginning. That is, they represent this beginning S and the ending string here. So the special tokens added by the tokenizer are mapped to none, and other tokens are mapped to the index of their corresponding word. So zero for the first word, that is this one. Then I have Einhorner, that is given 1. Now note one particular thing about these word IDs, which is, as per the documentation, they clearly said that several tokens will be mapped to the same word index if they are parts of that word. So here, this particular word Einhorner and the next token N, they are part of the same, both tokens are part of the same word, and that's why their word ID index are both 1, because they are part of the same one. And this property is important here. And why that is important is because that property will help us to mask some tokens. For example, here both these two tokens have the same word IDs given. So now for me, this next one, that is not important during training, and I'm going to mask it. And how I'm going to decide? It's because I can see that this is the same as the previous one. So we will actually write a method right now in a second to do this. Yeah, so that's how these word IDs method is pretty important in helping us to mask unnecessary things during the training. So now let's set -100 as the label for these spatial tokens, that is all these nonce, and also subwords where we wish to mask during the training. That is this kind of things that I just discussed. That is the second, this n over here. And why did I choose -100? Because it's pretty conventional. That the -100 is the ID to mask subword representation normally in many projects. That's because in PyTorch, the cross entropy loss class, that is torch.nn.cross entropy loss, has an attribute called ignore index, whose value is -100. This index is ignored during training, so we can use it to ignore the tokens associated with consecutive subwords. First, let's define a word IDX, and also empty list. Now for run a loop through word IDs, we have already seen this list is our word IDs in this case. So for word IDX in word IDS, and if word IDX is none, or word IDX equal to previous word IDX, then set the label IDs, append -100, else word IDX not equal to IDX, then label IDS, append labels word IDX. Okay, and okay, I need to, oh, that's label IDs, yeah. And then I also need to update the previous word idx to be current word. So let's set previous word idx. Cool. And if you have forgotten what labels are, these labels is this list. And how did I get the labels? That's because of this line right here. So we made two lists of words and labels taking from our random German DE example sentence. So labels are my NER tags, and all of these numbers actually represent NER tags because they represent the corresponding class IDs for their NER tags. All right. Okay, now let's print my label IDs to check if it worked. Oops, that's not how I wanted to. Oh yeah, I'm still in that loop. Yeah. Now run it. Yeah. So that's my label IDs. And now what I want to do is create my labels, create a pandas data frame. But to do that, I need a clear word IDs, label IDs, and labels. So let's define those things. So here I'm going to use our previously defined index to tag. And do you remember index to tag? Let's quickly check. Index to tag. That's our index to tag. It's a dictionary with all the keys and numbers and the corresponding NER tags. So my labels will be index to tag L. If L not equal to -100, else let's set it else IGN for L in label IDS. I think I have done some syntactical mistake here. Let's see. Index L. Yeah, of course. Here. Index to tag L. Yeah, that should work. Yeah. Similarly, I also need to define my index. Those will be tokens, then word IDs, labels, and now create a pandas data frame. And that would have my tokens, word IDs, label IDs, labels, and index will be index. Let's see if it works. Cool. So that's my data frame showing my tokens, then the word IDs, label IDs, and labels. And what I have done is initially all these special tokens I assigned this number 100, and also the subword that I don't need during the training I assigned them -100, and then for labels I assigned all those 100 to IGN representing ignore, because I want to ignore them during the training. So let's quickly see what I did in these last couple of steps with the example random German sentence. So first, so this is our German D example initial variable, which is a dict. And then I created words and labels from that, taking the tokens and NER tags. then I tokenized those tokens and also created my actual tokens by using XLM tokenizer.convert IDs to tokens. And then I applied these word IDs to get the corresponding IDs for each of the tokens. And finally, here in this step, I applied -100 to all the special tokens and also the sub tokens. For example, the second part of a same word. And finally, in these last steps, I replaced those -100 with IGN. And also use these index to tag in this case. So let's do all the 4-5 steps in a single util function so I can apply it on the entire corpus of a dataset, because these things I applied just for a single German sentence, but for the training I have to apply the same thing for the thousands and thousands of sentences or millions of sentences that I can have in the corpus. So let's define util function. Tokenize. So these function, what they are doing are tokenizing. So tokenize and also mask and also modify labels. And it takes an example sentence. Cool. First operation is tokenization of the examples. That would be XLMR tokenizer example tokens. True is split into words equal to true. Then define an empty list for labels. And then the next operation is going to be creation of word IDs and filling up this empty list of labels with label IDs. Okay, so I have to loop through enumerate of example linear tags. So for IDX labels in, am I doing it right here? Index and the labels in enumerate example, and I'm going to take NER tags. That would give me these key and values as index and labels. So my word IDs will be tokenized inputs dot word IDs batch index set it to IDX. And then so these word IDs that will return me a list mapping the tokens to their actual word in the initial sentence, and it returns a list indicating the word corresponding to each token. And then I'm going to do that assignment of -100 to some of the tokens if they are sub tokens, and also if they are already assigned a none value. So I have to do the same thing that I already did previous word IDX equal to none and label IDS equal to an empty list. And now special token, for example, those As and beginning As and ending As are mapped to none. That will be set to -100, and also other subtokens that I wish to not include in the training. So for word idx in word IDs. If we already did this in here, so it's the same code pretty much. If word x is none or word idx equal to previous word idx, then label ideas dot happened minus 100 else label, and I'm going to give word idx cool and update the previous token after the else clause. Previous word index equal to word index. And finally for labels dot append, that would be label IDs. And now tokenized inputs labels, and that will be my return from this function. Return tokenized inputs. Okay. And the next step is to apply these tokenized mask label function on an entire corpus of dataset. And for that as well, I'm going to have another util function that will make use of the famous map method of HuggingFace datasets to apply a function across all examples of a dataset. Actually, let's quickly take a look at the map method in HuggingFace official documentation, because we are going to use this map quite frequently in this video and also many subsequent videos in NLP domain. So just as the documentation says that some of the more powerful application of HuggingFace datasets come from using the map function. The primary purpose of map is to speed up processing function. It allows you to apply a processing function to each example in a dataset independently or in batches. This function can even create new rows and columns. And so when these remove columns option, there is a remove column option. Where is it? Anyway, there's a remove column option. You should definitely go through the documentation in more detail. When that is what that does is that it removes a selection of columns while doing the mapping. Column will be removed before updating the examples with the output function. That is, if function is adding columns with names in remove columns, these columns will be kept. And I am indeed going to use a remove column now. And also the benefit of using remove column is that it's faster because it doesn't copy the data of the remaining columns. Cool. Now, let's get back to my code and continue after where we left off. Yeah, so I'm now going to apply these tokenized mask modify labels to each example in a dataset. So my next util function will be encode, because we are using PANX datasets. And note that here we are taking the entire corpus. So return corpus.map And remember again, these tokenize mask modify labels is a perfect example of a processing function. That is, it is going to do some processing on my corpus. And that's where, as the documentation says, the map function is very useful because in terms of efficiency and faster execution, it's very important to use the map function when you are using processing function on an entire corpus. So return corpus.map and then tokenize mask modify labels badged equal to true. And here I'm going to use remove columns. And what are the columns I'm going to remove? They will be langs, NER tags, and tokens. Cool. Right. Now, okay. So now in the next line, I'm just going to be executing this. So pan xde encoded will become encode pan x datasets. Then to that, I will pass our previously defined combined panx dataset, panx ds combined. And from there, I am going to take DE, German set. Encode, oh yeah, I did not. Yeah, I didn't. Let's run after, yeah. Word IDs, key error word IDs. Okay, I think I have done a spelling mistake somewhere. Let me quickly fix it first. Yeah, so there was a small spelling mistake here. So anyway, now my panx DE encoded is the encoded form on the dataset. So this is going to be fed into my fine-tuning training model. Okay, now I also need to do few performance metrics related stuff. So for that, let's define performance metrics, and here I'm going to import this library seq-eval seq-eval dot metrics matrices. Import classification report. Yeah. So what it will do is it produces a nice tabular form of classification kind of report. So for example, let's take an example from their documentation. So what I'm going to do, just define two y true and y pred variables. Both are list of list. And then just print the classification report between y true and y pred. Let's run it. Module not found. Oh yeah, in Colab I need to pip install. Yep. Yeah, so now I've got this nice report. So classification report will give you the recall, F1 score, and precision for in a nice tabular format. Okay, so the seq-eval package expects the prediction and labels as list of list, which is what we provided here, and with each list corresponding to a single example in our validation or test sets. To integrate these metrics during training, we need a function that can take the outputs of the model and convert them into the list that seq-eval expects. So that's what I'm going to do now. So what I'm going to do now is to ensure that we ignore the label IDs associated with subsequent subwords. Okay, now I have got a nice report. So as you can see that from seq-eval, I get this nice precision recall F1 score in a tabular format. Just one thing to remember, that the seceval package expects the prediction and labels as list of list, which is what we provided here. So to integrate these metrics during our training, we need a function that can take the outputs of the model and convert them into a list of list format that seceval expects. And also remember, each of these lists corresponds to a single example in our validation or test set. So all these NER tags, they belong to a single example, single row in our dataset. And now coming back to the problem that I need to convert the output of the model into the list of list format so that it's accepted by the seceval package. Now, what is output of the model? Output of the model will be predictions and label IDs. So this prediction and label IDs will be my output of the model, and I have to convert the task right now is to convert these into the list of list format. Now, let's put another thing here. So when I actually took the output of this prediction and label, let's see the tensor form that the takes. So one second, let me take it from another file that I copied the output. Okay, so when I print eval pred.prediction, this we will come to this variable eval pred in a second. So the point is that prediction is the output of the model, and the tensor form that it takes is this kind of three-dimensional tensor. And similarly, when I printed my label IDs, these label IDs takes this kind of two-dimensional tensor form. And remember, these evalpred.prediction and evalpred.label IDs, they represent the y predicted value and y true value actually. So these are the predictions and true values, and that's the two things that we have to convert into list of list format. And so that's what I'm going to do now with the util function. This function will be slightly kind of tricky, but you have to understand the structure of this data here, that is eval these predictions and label IDs, and then it will be all clear. So let's define that. So the name of the function I will give is generate list for compute matrices. Compute matrix, and it will take predictions tensor and also the true label IDs tensor, which is just label IDS. Okay. First, I'm going to take my predictions with np.argmax. Threads will be from the prediction tensor. I need to take the argmax across the axis of 2. Remember, our prediction is a three-dimensional tensor, and the last dimension is where I'm applying the argmax on. And now I need to extract the shape of the spreads variable. So let's batch size and sequence length. These are the two dimension of spread. Yep. Also declare define two empty list. Label list and true labels list. This will be our final output from this function containing two list of list values. And now I have to start the looping and I have to run actually 3 loops, one inside another and inside another. So first out, the external loop will be over the batch size. So batch idx in range batch size. Sorry, batch example define two empty list here again for the labels and the predictions. So example labels, example threads will be two empty list. Now another internal loop over the sequence length. Sequence length is coming from this one, the second dimension of threads.shape for and here the job is to ignore uh, label IDs where it has been assigned the number 100 -100 as we discussed earlier, that they need to be ignored during the PyTorch training. So here as well, while I'm making this list, no element with a value of -100 should come. So let's put an if condition here. If label ID is batch index and sequence index not equal to -100. Oh, sorry, this is not length, this is sequence index idx, because I'm looping over each of the elements of sequence length. Yes. Here again, note to understand the way that I'm capturing or grabbing each element is uh, by this expression, because these label IDs is a two-dimensional tensor. This is the form or structure of our label IDs, and as you can see, there are many -100 within this two-dimensional tensor. So so the first dimension of this is batch index, and the second dimension, that is actual element here, is my sequence index. That's how I am grabbing each element. So to grab, for example, this particular 100, which is an individual element within this two-dimensional tensor, I need these two indexes, the batch index and then the actual sequence index. Yeah, so let's move on here. Label IDs, batch index, sequence index not equal to 100. Only then I am going to append that to my example labels or example threads. So example threads dot append. And here I'm going to make use of again index to tag, and as we know, this is our index to tag, which has each of the index number and the corresponding tags. So index to tag thread. Here again, I have to grab each element with the batch index idx and then my sequence index. You have to be very careful about these things here, because probably for any machine learning or deep learning project, you will be dealing with multi-dimensional tensors. So be very careful while grabbing each element. Yeah, batch index, sequence index, I think that's how it's work. And similarly, I have to do for example labels. Index to tag and there. So here it's a labels. Yeah, so I have to apply label ID, get it from the label IDs, and then I need similar to this batch IDX, and the next one for the actual element, which is sequence IDX. Cool. Why label IDS is showing me? Oh yeah, spelling mistake. LABEL. Yeah. Okay, so these three loops are over, and now I can, after this innermost loop, if condition is over, then I can update my final these two output variables, which are threads labels list and example threads, and similarly threads true label list dot append. To that I apply example labels. Example labels, LBELS. Okay. I think there's an extra S here. Okay, just put this S here, because they are list of list. And finally, return from this function just these two labels, threads labels, and then my true labels. Okay, so this function is over. Keep this cell running. Yeah, and next, so with that, all my initial setup is over. That is, all my data is ready, and this util function is also ready. So finally, now time to fine tune XLM-Roberta. Let's put a comment here. Yeah. So we now have all the ingredients pretty much to fine tune these, and so let's start coding. Some of the hyperparameters first. Number of epochs. Put that 3. And just to remind you the main purpose here again, that first our strategy will be to fine tune the base model on the German subset of PAN-X, that is PAN-X DE, and then evaluate its zero shot cross-lingual performance or zero shot cross-lingual learning on French, Italian, and English language. And for this, I am going to use the common HuggingFace trainer API. It requires some training parameters like what we are going to define here, like num epochs. Then I need batch size. So batch size, keep it at 24, and logging steps, that would be equal to PAN-X DE encoded. That's our training data set. Divide this by the integer length of batch size. That's our logging steps, and also model name. Let's give a model name. Let's give it because I'm going to use XLMR. So XLMR model name, which you have already defined, to that just append fine-tuned on PAN-X DE. Okay. Now the training args that should be defined, and I'm going to use these training train arguments, which is the name of the HuggingFace API, and it takes multiple parameters. So first one is output dir. which is where the train model will be saved. And I'm saving it in the same directory, and that's why I'm just passing model name to here. And these are my overall training arguments. And next, I'm going to do from equal dot metrics upon score. And I need another module from transformers called eval prediction. Transformers. And if we want to have a look at the documentation of this one, let's quickly go to yeah, so this is the eval prediction official documentation in HuggingFace, and what it does is, and this gives an evaluation output, always contains labels to be used to compute metrics. So this is the method that I'm going to use to get my output from the model for evaluation. And the parameters, it takes the normal ones: prediction, label IDs, and inputs, predictions of the model, targets to be matched. Yeah, anyway, so let's go back to, yeah. Yeah, so next I am going to have another small util function called compute metrics. It's very standard for any NLP projects with transformers. The function that this function will be used to compute metrics at evaluation. So let's define it. Matrix, and it takes an eval prediction object as the argument. This is of type eval prediction. Yeah, so now I'm going to use my earlier defined function, which was generate list for compute metrics, because here I'm going to get my y-pred and also y-true, and that's coming from so this y-pred and y-true will be in a list of list format, which will be accepted or will be passed to these sec eval package, from which the f1 score will be calculated. So to get this list of list, I am going to use that function that we wrote earlier, which is generate list for compute metrics, and that takes eval pred dot predictions and also the label IDs, and that's also coming from eval pred dot label IDs. Cool. And it returns, this function will return the f1 score, which will be f1 score will be calculated based on y-true and y-pred. Right. Okay. And next I am going to need data collator for token classification. So let's import that. From transformers, import data collator for token classification, and also I do need to define the data collator, which is just equal to I need to pass the XLMR tokenizer. Yeah. And yeah, so, and we need the data collator so we can pad each input sequence to the largest sequence length in a batch. Transformers provide a dedicated data collator for token classification that will pad the labels along with the inputs. So data collators are objects that will form a batch by using a list of dataset elements as input. These elements are of the same type as the elements of train dataset or eval dataset. And padding the labels is necessary because, unlike in a text classification task, the labels are also sequences. One important detail here is that the label sequences are padded with the value of -100, which, as we have seen earlier, is ignored by PyTorch loss function during the training. Now, another small function called model init required for the training. These are all standard function for NLP transformer projects. And this will have the first argument as our XLM-Roberta for token classification, which is our custom model from pretend XLMR model name. And pass this whole thing to device. Right. Finally, the actual training code, which will become, I think I have already, no, I have not imported the trainer, so first import transformers. That's the trainer, and then that will have the model init equal to our earlier method model init. Args will be, and you can see these all the arguments are here of the transformer trainer class. So right now I need to provide the args, which we have already defined to be training args. Now, okay, the next one is data collator, which is my data collator. Compute matrix is again equal to our earlier defined method compute matrix. And what else? I need the training data set, I need eval data set, and tokenizer. So all these are the rest of the arguments. And finally, the actual training execution, which will take almost like 15 to 20 minutes with GPU trainer.train. That is all. And we have already defined earlier within our training args here that the number of epochs as 3. So it will continue for 3 epochs. Let's wait and I will come back after the training. All right, now my training completed for 3 epochs. It took around 15-20 minutes with the 16 GB GPU in Colab. And yeah, so let's now print some results. And these are the final results as the output of the training. So training loss 0.1548 matrix. Do I get a F1 score here? Train loss, total floss, epoch 3. Okay, now just print our important parameters in a data frame. So what I'm going to do, create a data frame. Create a data frame. Trainer. Remember, trainer was the variable name that we defined earlier, which is coming from here. That is, trainer was defined to be an from this trainer class. So I have all the history, all the status, all the important variables and parameters saved in this trainer variable, and I'm going to access that now. So what I'm going to do, trainer dot state dot log history. Sorry, there is no. And from here, I'm going to take a list of epochs, then loss, eval loss, and also f1, which is eval f1. And how did I get this log history? You can just print the trainer.state, and that will give you all the parameters that it has within it. So this trainer.state will give you so much information you can see here, and within that there is one metric called log history. So this is a list, as you can see right here, and you can get a lot of information from here. And from this log history is where I'm getting epoch loss, eval loss, all these things you can see here, eval f1, etc., etc. Yeah, so that's how you get it. And now I am going to rename some of the columns in this data frame. That's my renaming. So I'm just renaming epoch to epoch loss to training loss, just to make it a little bit more meaningful. And then I have to change the epoch in a little bit differently. Epoch will be df just a lambda function here, lambda x round x. And I also need to do little changes in my training loss. Df if fail, and df validation loss also the f1. So I have to wrap it within another list, df 1 second. So this will be bfill, and also chain it with ff fill. And finally, df.drop duplicates. All right. So about these ffill and bfill, the ffill method replaces the null values with the value from the previous row or previous column if the axis parameter is set to column, and the bfill method is used to backward fill the missing values in a data set. So it will backward fill the nan values that are present in the pandas data frame. And after I run this cell, I get this data frame, which will show me the training loss, validation loss, and F1 score for each epoch. And we can see we get pretty kind of good results. So at the end of my 3 epochs, the F1 score was 0.86. Okay, now finally test this fine-tuned model to do a simple German translation. So let's get random German sentence Yeah, so this German sentence I just got from a Google search, and it actually means that Deutsche Bank is headquartered in Frankfurt, and this is the German form. And we are going to tokenize this sentence with our model, that is a fine-tuned model. So I'm going to use that util function get ner tags from text and model that we wrote earlier. To that, I need to pass text de, then my tags, and this trainer is our trained variable. So this is where from here I'm getting the fine-tuned model. And lastly, the tokenizer. Here. So this model is supposed to give me this data frame, and we can see that this sentence has been tokenized with our fine-tuned model. And we can see, looking at these, that the Deutsche has been identified as B org, that is beginning of an organization. Bank also has been I org. Frankfurt, as expected, it's a B location, beginning of a location. So it seems to be working fine on a random sentence. And now I'm going to do some basic error analysis on our validation dataset. That is, the training was done on the training portion of the dataset, and now I'm going to do a very simple error analysis on the validation part. And remember, when the model, the error analysis here, I'm going to do a very simple and very basic error analysis. But in actuality, it's always better to do an exhaustive error investigation, because when the model performs worse than expected, looking at the errors can definitely yield useful insight and reveal bugs that would be hard to spot by just looking at the code. And even if the model performs well, even in that case, there are no bugs in the code, error analysis is still useful tool to understand the model's strength and weakness. So before that, let's quickly define our validation dataset. Valid set batch would be nx, that was encoded, and take the validation part only, and let's just print this to see what this contains. Yeah, so we have 6,290 rows in the validation dataset, and the features are input IDs, attention mask, and labels. Now we can also check valid set batch dot features. I'm just checking that everything is working as expected before I build my util function. Yeah, so features gives me a dict form of data structure which has attention mask, input IDs, and labels, and all are sequences. Cool. Now, yeah. So what I'm going to do, I am going to build a util function here. And what this util function will do is produce the loss for the validation dataset. Because we already have the fine-tuned model, then I can apply this model on the validation part of the corpus, and that will produce a loss for the validation dataset. And in this function that I'm going to write now, that will just present a data frame showing the input IDs, attention mask, and the labels of the validation dataset with the corresponding loss and the predicted labels row wise. So let's start doing the code for that model. I need cross entropy for calculating my loss. So NTROP PROPY cross entropy, and then my model get forward loss and predicted label. So just name it loss and label, and it will take a batch of inputs. So first convert the dict of list to a list of dicts suitable for data collator. Features will be equal to, I'm going to do a list of dicts. So dict, then zip batch and t for t in zip asterisk batch dot values. That's how we will get the values. Okay. Yeah. Now I'm trying to pad the inputs and labels and put all tensors on device. So for padding, I need to get data collator that we have defined earlier from the data collator module. So batch should be equal to features. From the batch, I will get input IDs, transfer them to device. Similarly, similar kind of things I'm going to do for attention mask and labels as well. Mask, batch. We already saw that how I'm getting these input IDs, attention mask, and labels, because we know that these valid set batch.features has these three features: attention mask, input IDs, and labels. Yep. And labels. Mm-hmm. Is the spelling correct here? F-E-A-T-U-R-E-S. Yeah, looks like it's correct. And now I need to loop through. I need to apply the model, train model on the input IDs and attention mask. But I am going to define a context manager here, which is I do not need the torch.gradient. So because I'm just in the evaluation mode. So what I need to do is pass data through the model, trainer.model. And this is a model that we have trained already. And now I'm just going to evaluate the model on the validation set. So output will be equal to trainer.model. To that, I pass input IDs and attention mask. Now I need to get the predicted label, which I can get from the output logits, and I need to apply argmax on the output logits. So because the predict class with the largest logit value is the one that I'm interested in. So predicted label equal to max output dot logits along the axis of -1. That is the last one. Dot CPU. This is a CPU based operation to apply numpy here, because it's just CPU matrix and I need to get the numpy array. So that's a way to get it. What else do I need? So my predicted label is there. So now I can calculate the loss because I have the true value and also the predicted value. So come out of this loop. So the loss calculation is per token after flattening batch dimension with view. So I'm going to flatten it. Loss will be equal to cross entropy and output logits dot view. The first dimension is inferred and the second dimension is a number of classes, and we have 7 of them. And then I also need to flatten the labels. So this whole output.logits.view, this is part of the prediction. This is a predicted y, and now I'm passing the true y. Labels.view. Reduction equal to none. Okay, now loss equal to, I'm getting in input IDs here. No S over there. Yep. What is this? Loss is not defined. I don't need to define loss here. Yeah, anyway. So loss equal to loss.view. Here I'm unflattening the badge dimension and convert to NumPy array. So loss.view, and then for unflattening, I need the length of the input IDs. Len input IDs. Then the last dimension is inferred, and then do CPU and then dot NumPy. Yeah. So that's my loss, and finally from this function return, I'm going to return loss and also predicted label. And I'm returning these values as a dict format. All right, now trying to apply this method that we just wrote. So valid and I'm going to use the map method again. So valid set batch. On this data set, I'm going to apply that method with dot map. Label that. That size equal to 32. And now convert it to a data frame. So valid lost. I'm going to use 2 pandas and then just print the df.head. Run this cell. It may take 1 or 2 minutes because it's doing this prediction and evaluation on the entire valid dataset. So let's give it time. All right, after finishing the above df.head line, this is the output that I get. So this data frame contains predicted labels and the loss on the validation dataset based on our fine-tuned model. So this is the evaluation result or basic error analysis after we fine-tune the model. So we can see the first 3 columns were already there in the validation dataset, which is input IDs, attention mask, and labels. These 3 columns are already there, and the new columns that were added after the evaluation method is this loss and predicted label. So this loss is the predicted loss on the validation dataset after applying our fine-tuned model, and this is the predicted label. Okay. So that was our very basic error analysis and also checking, applying the fine-tuned model on the validation dataset, validation corpus. And now it's time to do zero shot learning or getting prediction from other language dataset based on our fine-tuned model on German dataset. And for this cross-lingual transfer or zero-shot learning, since we plan to evaluate multiple languages, that is Italian, English, and French, let's create a couple of util function indeed to help us in this method. So first one is get F1 score for a data set. Trainer data set. Trainer data set matrix. Matrix will be test F1. And we can use this function to examine the performance on the test set and keep track of our scores in a dict, in a dictionary. So F1 scores, I'm again using default dict. F1 score DE of my 1 second. So here I'm just printing the F1 score on these D dataset. And when I ran that cell, I got this F1 score on D model dataset is 0.869. All right, so that F1 score of 0.869 is not too bad. And now I want to have another util function which will do this kind of F1 score production for various languages. So this util function will take two arguments, one for the language and another for the trainer variable. The trainer variable is what we get after fine-tuning a model. So let's just write that. Evaluate lang performance. It will take a lang argument and also trainer. Sorry, because we are always working with encoded panics. So encode, was it encode panics? Oh yeah, I think so. Encode panics dataset and dx combined, and to that I pass a lang. Actually, this was encoded panics dataset. Okay, anyway, so panics.ds, and then it just returns the F1 score, and for that I use our previously defined function get F1 score. Trainer and panics.ds test, because the F1 score is on the test dataset for evaluation purpose. Cool. Now let's see its results as well. DE FR. That is, I'm taking the French dataset. Evaluate lang performance. Lang will be FR. And trainer remains the same. This is a variable that we defined after the fine-tuning of the model. And let's just print few parameters. I'm just printing here the F1 scores DFR. And when I ran this cell, I got this output. Right now, I'm just copying it from another Colab notebook because that Colab notebook is right now busy doing some of the GPU operations. So I do not want to disturb it. I'm just copying the result output from that Colab notebook here. So this is the F1 score I got on French dataset, and we can see that there is a drop of about 15 points in this matrix here. Remember that our model has not seen a single labeled French example because our model was completely trained on the DE, that is a German dataset, but it still produced F1 score on this French dataset of 0.702. So that explains more or less the reduction in the value for the F1 score here. And in general, the size of the performance drop is related to how far away the languages are from each other. Although German and French are grouped as Indo-European languages, they technically belong to different language families. Normally, it is called Germanic, and the French fall into the Romance, respectively. So yeah, so that's another reason for these reduction in the F1 score for this example of zero shot learning. Because, and again, zero shot learning here is because the training was done on German dataset, but that trained model was applied on the French dataset to get this F1 score. And now similarly also check the F1 score for Italian language. So it will be the exactly similar code. Let's see. And now it's Italian. Evaluate lang. And then I just print the F1 score. And let's see how much do I get. Okay, so the F1 score for Italian, we get 0.674. So it's even less. Okay, so that was our F1 score. We can actually do the same for English as well. Let's just do that when we did that. Yep, so this is for English. So only changes is that I'm passing en as a language to this function. And let's see. And for the English language, zero shot learning F1 score we got is even less, which is 0.592. So now a fundamental question, that when does a zero shot transfer make sense? So far we have seen that fine-tuning XLM-Roberta on the German corpus yields an F1 score of around 85%, and without any additional training, the model is able to achieve kind of modest performance on other languages in our corpus. So now the question is, how good are these results and how do they compare against an XLM-R model fine-tuned on a monolingual corpus instead of these multilingual corpus situation? And by monolingual, I mean that to get an F1 score on the French dataset, we will train the XLMR model on a French dataset itself. But here, the case was that we trained the model on German dataset and was getting the F1 scores on French dataset, on Italian or English dataset. So in this section, in the next section, I will explore this question for the French corpus by fine-tuning XLM-R on training sets of increasing size. And by tracking the performance this way, that is getting the F1 score of increasing size of corpus, we can determine at which point zero-shot cross-lingual transfer is superior, which in practice can be useful for guiding decisions about whether to collect more label data for a specific language or whether we should just do zero shot learning, that is training on a single dataset and then transferring that knowledge to other dataset. And for the purpose of the next section, for simplicity, I will keep the same hyperparameters from the fine tuning run on the German corpus, except that we will tweak the logging steps argument of training arguments to account for the changing training set sizes. We can wrap these all together in a simple single utility function that takes a dataset dict object corresponding to a monolingual corpus, then downsamples it by a particular factor and fine tunes XLM-Roberta on that sample to return the metrics from the best epoch. Let's implement that, then it will all become much more clear. Encode an X dataset. To this function, I just pass our combined panx dx, panx ds combined, and then take the French one. Okay. And I also need to define the matrix df, that is the result of the fine-tuning training on single corpus on the pan French encoded, panx French encoded. That's the output that I'm calling here matrix df, and that would be the output of fine-tuning training on single corpus. To that I pass panx before encoded. Yep. So matrix df. Let me write this code and then we will run all this together in Colab, because it needs GPU. So yeah, so that's my matrix df. All right. And now I am, just like I discussed that here my purpose is to show the F1 score for different sample sizes. So I am going to run these fine-tuning training on single corpus, this particular method on the training dataset for various sizes of samples. Oh, I see. I missed giving the second argument to this function, which is the number of classes, and no, sorry, num samples. Let's give it 250. Yeah. And when I run this cell, this is the output I get. So this is the F1 score for the after the 3 epochs, and we can see the F1 score is pretty bad here. That's because the num samples were extremely small, only 250. This is like a very low numbers for the number of samples. So the next step, just as we discussed, we will see how this F1 score improves when we increasingly take more and more number of samples over by running a loop. Let's write that code. $500, 1,000, 2,000, and 4,000. So I'm going to run the same fine-tuning training on single corpus, this method, this training util function for all these different number of samples. Matrix df happened, and that's where I'm going to take this method. Okay. And this method takes the panx fr encoded and also samples. Ignore index. Good. And let's see the output of this, which is saved in a separate notebook. So here we see as we increase the number of samples, the F1 score gradually improves. So this is for the first one, first result, and then the next loop I get a higher F1 score for the same number of epochs, and then continue. Here my F1 score improves even further. I think this is for the 2000 number of samples, and I finally also get this is I think for the 5000 num samples. You can see the F1 score at the end of 3 epochs is really really good, 0.84. So let's actually plot this increasing value of F1 score in a with matplotlib. So that means that will be much more cleaner to present this improvement. So big plot dot subplots. So I will keep one line for the zero shot learning. That is when we trained on German dataset and applied that same trained model on the French dataset. That was the case for zero shot learning, and so we will keep one single line in this plot to for that F1 score, so that we can compare that whether zero shot is giving better result or whether monolingual training on specific dataset, relevant dataset that is, gives better result. So F1 score. So that was our DEFR. That is trained on DE and then applied the trained model for zero shot transfer learning on French. Let's keep the color of this line red. Color equal to R. Matrix D, DF. Let's define the legend. That would be zero shot learning from German dataset, and fine-tuned on French DS. LOC equal to lower right. Number of training samples, and plt.y label would be F1 score. Finally plt.show, and let's directly look at the output. So here is the output that I got for that code. And so the important thing to see here is that this red line is what represent my zero shot from the Deutsche, that is a German language. And this blue line is what our monolingual training on the French dataset. And we can see when the horizontal line represents the number of samples. So when we initially started with 250, our F1 score was really, really bad. But as we increased the number of samples, F1 score really substantially started improving. And at one point, it exceeded the zero shot learning F1 score. So what we see mainly from this plot, that the zero shot transfer learning remains competitive until about 750 training example, that is around here. So I'm looking at the vertical point right here. So this pretty much around 750 number of samples. After this point, fine tuning on the French, that is this blue line, reaches or goes beyond the zero shot learning, and that's the main point that I wanted to show here. But remember that although we clearly see that training directly on the French dataset gives us improved result when the number of samples increases, but remember that getting domain experts to label even hundreds of documents on a particular language can be very costly, especially for jobs like named entity recognition, where the labeling process is fine grained and time consuming. The cost actually increases to get some language experts to really label a particular language dataset, and that's where the zero shot learning comes to play to save us. That is, we can just train on a single corpus and then apply that learning to other corpus, other language corpus, and that gives reasonably good result. Of course, when the number of samples really increases, zero shot learning gives, I mean, the fine tuned on the specific language gives better result than zero shot learning. But for a normal case, for a regular situation, when you do not have that much of data, labeled data on a particular language, zero shot learning is the way to go, because that gives reasonably good result. And now that this plot is over, another technique actually we can try here to evaluate multilingual learning is to fine tuning on multiple languages at once. So instead of training just on German languages, we will train on multiple languages and then see what kind of zero shot transfer learning F1 score we get on different languages. And now for that multilingual training, I have to concatenate multiple corpus. That is, I have to concatenate German with French, with Italian, with English. So let's just first quickly see that what a single dataset structure is in our dataset dict format in HuggingFace. So PAN-XDE encoded, this is how the structure is. It is a dataset dict structure, as you already know, because this is the structure we are working with right from the beginning, and it has train, validation, and test. So this is a single corpus. Now we have to concatenate multiple of this kind of corpus. And also remember, if I do something like this, that is PAN-XDE encoded.keys, I will get the train, validation, and test. That is the three separate splits of dataset I will get. And these two structure we have to remember when combining or concatenating dataset. And for concatenating, I need to import a module called concatenate datasets. Import datasets. And now I'm going to write util function for doing this concatenation job. Concatenate splits. It will take a corpora which will have multiple corpus, and this, remember, this corpora will be a list, and each of the element in that list will be one single corpus. So it's a list of corpus. So first define dataset dict corpus equal to, oops, spelling missed, dataset dict, then run a loop for train val test in corpora. Take a single corpus from that list of corpora and then take the keys. That will give me these splits, that is train, validation, and test splits. corpus train test val will be equal to concatenate datasets. To that, I pass corpus. Corpus is a single corpus in that dataset. So corpus, it will be again the split. So the corresponding split, whatever it can be, train and test or val. Train, test, val for corpus in our program. List comprehension. And I need to shuffle it as well. Just a kind of practice you're following with a seed of 42. Yep. Now out of the loop and return this multi-corpus. Okay. Multi-corpus, yeah. And then apply this function or execute this function to get my panxdefr concatenated encoded. Let's make it equal to concatenate splits, and to that I pass panxde encoded and also panxfr encoded. So then that means this output will be a concatenation of these two datasets. Right, and next I have to start the training configuration, etc. So just as we did earlier, training args dot logging steps, that would be len of panxdefr concatenated encoded train that divided by batch size. Similarly, I need to actually I should just copy it from my earlier configuration, and let me do that. Yep, that is all the configuration. I'm just following the regular practice that we have done earlier for our earlier training. So these are all the training configuration, and only change here is the name of the output dir. I am naming it as XLM-Roberta base fine-tune panxde and fr, because now we are training for both Deutsche, that is German, and French data set. And when we run this trainer.train, let's see the output of that. And this is the output of our this particular training where we concatenated the German and French dataset. We can see the F1 score after the end of 3 epochs is pretty good, 0.86. Now, what I need to do is I need to check, just as the purpose of this was that we will train on this concatenated dataset, and then we'll check how this new model performs now in terms of zero shot learning on some other dataset. So given that we have trained it on German and French dataset, I'm going to calculate the F1 score for the evaluation on English and Italian dataset on which they were not trained. So let's do that. So I'm just looping through the list of languages that we had defined previously. And I'll be applying our evaluation util method that we have defined earlier to get the F1 score on various languages. So F1 will be equal to evaluate lang performance, yep, lang and trainer. Right. And then I'm just going to print the result. That is all. Cool. Let's check the result. Now see, output of that particular this code, that is this looping code, will give me, because I'm looping through the languages, and these languages actually contain the German, French, Italian, English, all these 4 data set. And see the F1 score. So F1 score of DEFR model on DE dataset, that is, this is DEFR model, means our concatenated model that we just did the training on. And F1 score on this model on the German dataset is 868, 0.868. Now for the next one, F1 score of DEFR model on French dataset is 0.858. And then the next one, this is interesting. So this is the out of the now they are predicting the F1 score on Italian dataset, which was not part of the original training dataset. And this is where the zero shot learning comes into play. So F1 score of DEFR model on Italian dataset is 0.797. And the last one is on the English dataset. Again, an application of zero shot learning here, because English was not part of the original training dataset, and I'm getting an F1 score of 0.668. So overall, what we observe is that it performs, that is, this multilingual model performs much better on the French split than before, matching the performance on the German test set. But interestingly, its performance on the Italian and English splits also improves by roughly 10 points. So even adding training data in another language improves the performance of the model on unseen language. And that's the very thing that I wanted to check with this multilingual concatenated training dataset. So now we are kind of nearing the end of this video. So let's round out our analysis by comparing the performance of fine-tuning on each language separately against multilingual learning on all the corpora. So since we have already fine-tuned on the German corpus, we can fine-tune on the remaining languages with our function, the util function that we wrote, which is fine-tuning training on single corpus function, with num samples, that is number of samples, equal to the number of examples in the training set. This is, I'm just initializing this corpora variable with a single dataset called pan x de, and then over the next few lines I'm going to append other dataset to it. So remember, while I'm adding dataset to these combined corpora variable, I am going to exclude the German from iteration. So for lang, in this languages variable includes German as the first element. So to exclude the first element, I'm just starting from 1 and then slice. Okay. Now tree. I need to modify the output directory because there will be many languages. So just change the name to be annex. And here I'm going to give the corresponding language. Now I need the DS encoded, that is an encoded dataset for this monolingual corpus. So I'm going to use these earlier defined method, encode panx dataset. Combined. From that, I take the corresponding lang. And then finally, the actual training. And for the actual training, I'm going to use the same function that we previously defined. Where is it? Anyway, the function name is fine-tuning training on single corpus. Let's just quickly have a look at this. Yeah, this is where it is defined. So this fine-tuning training on single corpus, as you can see, it is defining this all the training configuration that is that will be passed to the trainer class, and then it is running this trainer.train. So this function actually has a responsibility of executing the whole training. And right now in this code that I'm writing, there I'll be doing that, I'll be executing this function for each of the language except German, of course. So that's the reason this training will take a long time, because it will run the full training with 3 epochs for each of the languages. So that means if I have 3 languages here, and there will be total 3 into 3, 9 epochs, and it will take almost 1.5 hour to 2 hours to train. So fine tuning training on single corpus, and then I pass it the corresponding language encoded, of course, and then ds encoded train, because that's my training data, num rows, and then collect my F1 scores in a common dictionary, because this matrix variable will have the F1 score. So my F1 score matrix matrix F1 score, and then take the 0th element. Yeah, and finally add the monolingual corpus to list of corpora to concatenate. Okay. Okay, the training went on for almost 1.5 hours in Colab with a 16 GB GPU. And so now that we have fine-tuned on each language's corpus, the next step is to concatenate all the splits together to create a multilingual corpus of all 4 languages. And as with the previous German and French analysis, we can use the concatenate splits function to do this step for us on the list of corpora we generated in the previous step. This is the corpora that we generated. So let's do corpora encoded equal to concatenate splits corpora. Okay, now we have our multilingual corpus, and we run the familiar steps with the training. And what are the familiar steps? Just define all the training args and configuration. Training args dot logging steps equal to len corpora encoded. Take the train, divide it by batch size. Similarly, I have to define the output dir. But before proceeding, just want to clarify one thing very clearly here, because otherwise it may get confusing. What in these lines I'm doing is 2 things. This corpora variable will have the individual encoded dataset, but this matrix here, that will have the F1 scores after fine-tuning XLM-Roberta on each individual separate corpus. So this matrix will have the individual F1 scores, but now in this next cell, what I'm going to do, I'm going to fine-tune or train again, but this training will be on the entire corpora. That is, this training will be on all the different corpus together concatenated. And the purpose of doing this, so there's 2 training indeed. This line here, let me clarify, this line right here, that's doing the training on individual corpus. But the cells here that I'm going to write right now, that will be doing the training on these concatenated corpora encoded. And then after these two trainings are done, I'm just going to compare the F1 score, that which one gives more sensible F1 score. That is whether it's better to concatenate all the individual corpus together or train them individually to get a better F1 score. So that's the main purpose. So there's two set of training going on here. Again, repeating, this matrix is doing the individual training on individual corpus, and the cells that this cell here, I'm going to do the training for the whole corpora together. All right, and this is that whole training code for doing the training on the entire corpora. That is a concatenated data set. And after doing this training, this also took almost 1 hour to complete, and I got these F1 scores after the 3 epochs. And now I am going to get the F1 scores for these training on the entire concatenated corpora. So I just need to enumerate through the languages list for IDX. Languages. Remember, these languages has 4 individual language in it's a list. So I can get the F1 score matrix updated with the because now the entire training is done on the whole corpora. So I can update this F1 score matrix with the variable called all, because this is this F1 score is for all the languages together. Get F1 score trainer, and also it takes corpora dx, and this is the test evaluation dataset, test dataset. Yeah. So basically, what's happening in this F1 score is that as you can see, I'm mentioning all. That means the training was done on all the 4 languages together, all the 4 corpus together, and then the second element here, I'm passing the languages. That means, although the trainer variable comes from these model, which was trained on all languages, but then the F1 score is being calculated on an individual language, and that's what the second element makes sure that particular thing. And here also I am passing corpora idx, which idx means it will I'm iterating over here, so it has 4 elements, so it will go through the 4 languages and then apply the corresponding languages test set and get the corresponding F1 score. So this F1 score, this variable now will be updated with all the 4 different sets of F1 scores for different languages. And what I just said here, that will become more clearer once we present the data in a proper pandas data frame in a tabular format, where there will be a matrix and there will be rows and columns, and we'll show that how the what was the base the model was trained on, whether it's an individual language or the combined language, and what was the different F1 score we got on different languages. So let's build the data frame, and we have to be careful here to select the proper variables. So first, scores data, it will be a dict, and the key is DE, that is a Deutsche part, and there it's coming from F1 score DE. All right. Now, each language I have to loop through, I have to do a list comprehension kind of thing here over languages variable. So each, let's do a dict here, lang F1, sorry, that's F1 scores. for lang in languages. Lang in languages, yeah. And lastly, the all variable. If one scores all, okay. Yeah, so that's the scores data. Now F1 scores DF. That will be a PD dot data frame scores data. Need to transpose and also round 4. And now I need to rename a few of the axes and the column names. So F1 rename axis. I'm tuned on columns equal to will be evaluated on in place equal to true. Now just show this data set. Yeah, data frame. Yep, that should do. And this is the result. And looking at these data frame, now it's I hope it's becoming completely clear that what we wanted to achieve, that all our training were on different base data set, and our F1 scores was calculated in different situation on different languages. And what were the different situations? The different situations were that we calculated this is the important thing, that is fine-tuning was done firstly on German dataset, then on each of the individual dataset, and ultimately on all the datasets concatenated together. And then this is the F1 score we got. So when we fine-tuned on only on German dataset, the F1 scores on German dataset, that is now you're looking at column, F1 score of DE column is 8691, F1 score on French column is 7016, and Italian 6739, English 0.5921. Now when we fine-tuned on each of the individual dataset, then DE F1 score is 8691, and this, as you can see, this 8691 and 8691 matches because here also the fine-tuning was done on Deutsche or German, and the F1 score was also calculated on the German dataset. So the training and evaluation was done on the same dataset in both these cases, these here and these here, and so obviously the F1 score is same. Similarly, here look at this element here, this cell here. The training was done on the French dataset, and that is a fine-tuning was done on the individual French dataset, because here I'm looking at the each row. Each row means each individual corpus was the training dataset. And because I'm looking at the French column here the fine-tuning was done on the French corpus, and also the F1 score was calculated on the French dataset test, that is evaluation part, and I got an F1 score of 8372. Similarly here, the fine-tuning, that is the training, was done on Italian dataset, and also the F1 score was calculated on the Italian dataset. Now, if you are confused, just look at this number 6739 and 0.8178. Let's understand what is the difference. So look at the first column, first row here. In this case, for this number 6739 here, the training, that is a fine-tuning, was done on German dataset, but the F1 score was calculated on the Italian dataset. So it's a perfect example of zero-shot transfer learning. But for this number here, that is a F1 score of 8178, the fine-tuning, that is a training, was done on Italian dataset, And also the F1 score was calculated on Italian corpus. So this is not really a zero shot learning. And obviously in this case, we got a higher F1 score. And finally, this row here, the fine tuning was done on the final, our final, as you remember, our final training was here, which was done on the corpora encoded. And that means here, all the concatenated dataset was responsible for the training. That is, all the entire concatenated dataset was passed to the training code. And then we calculated the F1 score on individual languages, and that's the F1 score we are getting here for different cases. So overall, from these results, we can draw a few general conclusions. Like the multilingual learning can provide a significant gains in performance, especially if the low resource languages for cross-lingual transfer belong to similar language families. And in our experiments, we can see that German, French, and Italian achieve similar performance in all the categories, suggesting that these languages are more similar to each other than to English. As a general strategy, it is a good idea to focus attention on cross-lingual transfer within similar language families, especially when dealing with different scripts like Japanese or Chinese, etc. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So, see you in the next one. Thank you very much for watching. Hey everyone, this video is about sentiment analysis on a text corpus using the famous FinBERT model from HuggingFace. And the basic issue we are going to tackle here is that we know that BERT has a max length limit of tokens equal to 512. That is a maximum number of length of token that BERT can take or will accept is 512. So if an article has a length much bigger than 512, then how do I deal with that? And just like in any other problem in software engineering or machine learning, there are a couple of ways to deal with this situation. And here in this video, we will see one of them. So let's start. And initially, I import the regular ones, BERT for sequence classification and BERT tokenizer. And next, I am going to define my model and tokenizer. So just like I was saying, I'm going to use this FinBERT from HuggingFace. You can check out their official documentation. It's pretty popular model with, I think, more than 1 million downloads. And a reasonable size, something like 420 MB, 450 MB around. So it's pretty easy to deal with in your local machine setup. All right, now first thing I'm going to do is define a little util function which will get the predictions. Let's define it. So this function will just take tokens as its argument. First, get the output. These are all regular steps probably you are familiar with if you are using HuggingFace model. So I'm just passing the tokens to the model to get my output. Now this will give me logits, but I need to convert them to probabilities. So my probabilities will be equal to torch.nn.functional.softmax output 0 over the last dimension, dim equal to -1. Now for the text corpus, I have copied text from a random Google search on Bitcoin regulation. So this is my text. It's pretty long one, and what I have what I've done is that I have copied it from this source. So I've given the source here. You will get it in the in my source code in GitHub. So this is just talking about the future of crypto regulation. And because I'm using FinBERT, and that's why I was trying to search some news or article related to financial world. So given that text, now I can actually generate my tokens, because we already defined my tokenizer at the top. Tokenizer.encode class. At spatial token, I'm keeping it at false. I will come to this point in a second, that why I'm keeping it at false. For now, just go ahead and print my token. Oops, I did not run this cell. Yeah. All right, so this is a very large tensor indeed. And we can see that it has got one key as expected, input IDs, and it will also have another key called attention mask. Actually, it will have token type IDs as well. Let's just print the keys so that I can actually check them. Yeah, so I have three keys here: input IDs, token type IDs, and attention mask. Let's quickly check the length of the input IDs. Token. Sorry, that's tokens. That's really large, 1653, but our BERT model can handle 512. So here is the issue that I was talking about. Okay, now let's see that how we deal with it. But first, note that there, like I was saying, there are mainly two approaches by which this kind of situation is handled. That is when the token length is much more than what BERT can cover. So the first approach is to using neural text summarization to shorten the text to below 512 tokens. And the second approach normally that is used is to create a window, a sliding window indeed, which will slide across the text corpus, and that window obviously will be less or equal to 512, and then calculate the average of those multiple windows after I slide that window over the entire text corpus. And here in this video, I will be using the second approach, that is the sliding window approach. So the window in question will be a subsection of our tokenized text of length 512, and then I will slide it over the entire 1653 number of token length. And a couple of points to mention here. For example, that during the tokenization, I used add spatial token equal to false, because this will, if I had it true, then this will add CLS, that is a classifier special token, and also the separator, that is a ACP special token, to the start and end of the full tokenized text. But in this case, I do not want that, because I'm going to create from this entire text, I'm going to create many windows of text, that is many chunk of text, and then I will add it to each of those chunk at the beginning and at the end, these CLS and the ACP token respectively. But that I will do with a separate util function. And also here for this, in this case, I will not specify the max length, truncation, or padding parameters while dealing with BERT, which are like the most often used parameters while you are working with BERT. Because max length, truncation, and padding in this particular case will not be relevant. And also we will return a standard Python list rather than tensor by not specifying return tensor. So if I specify, you normally return a tensor that is either a TensorFlow tensor or a PyTorch tensor. But in this case, this will make, in this case, I will be only returning a normal, regular Python list. and that's why I'm not using return tensor. And the reason for doing that is mainly because that I'm going to do some manipulation here, and if I initially return a PyTorch tensor, that will be problematic for me. So what I will do after my manipulations are done, then I will convert the regular list back to PyTorch tensor, which you can definitely do. And yeah, so that's a kind of approach I will be following. So, and you can check that these input IDs normally are these tokens normally are tensor. That is, if you specify return tensor, but in this case, we can check that they are not really PyTorch tensor and they are just list by doing this type tokens input IDs. Yeah, that's a list. That's how I wanted it. Yeah. So now let's define a couple of variables. Also, I need to do it for attention mask. Yeah, there are some. Cool. And so now, yeah, so that's our input IDs, and we can just see again that input IDs are actually what they are. So let's just print the first 10. Yeah, so that's my input IDs. Okay, now we will be using some code to break our list into smaller section. And actually in this cell I will be writing some code to just break the entire corpus into different start and end section, that is chunk of text. So first I need to define starting and ending position, and because I'm using FinBERT and FinBERT can take maximum of 512 tokens, so I'm going to start at 0th index and my window size will be 512. Start equal to 0. Window length will be 512. Now get the total length of our tokens. Now initialize a Boolean variable, because I'll be running a loop. So just initialize a Boolean variable to control the loop, because at some point I need to stop the loop. So all I'm doing in this cell is just segmenting the entire text corpus into different start and end. And I just want to see that that's working. So I'll be printing start position, end position for the entire length of the corpus. So that's what this loop is about. So first, the end position will be simply starting from the starting position plus the window length. And if the end position is greater than the total length, make these our that's where the looping should end. So if total length I'm setting the loop equal to false so that the while loop will stop executing any further. And change our endpoint to the final token position in this case. All right. Total length. Okay. This is where the if condition end, and now I just want to print the start and end position. And after this, I also need to update the start position because the next start will be the end. That is start equal to end, because this is a sliding window. So the ending of the first sliding window will become the starting position of the next sliding window. Okay, now just run this. Cool. Yeah, so that's how I wanted it. Remember our total length of the, what was the total length? Length of token was 1653, and that's what we are getting at the when the sliding window ends. Okay. All right, and now I'm going to write the most important key function in this exercise, and that is the function that I'm going to write now will chunk the text to window size and predict the probabilities by applying the FinBERT model on each chunk. So basically, what I'm planning to do is to extract the window from my input IDs and attention mask. Then for each window, I need to add the special tokens of CLS and ACP. That is the classifier token, which is which has a class ID of 101, and also the separator token at the end, which has a class ID of 102. So I have to add these CLS and separator token, that is CLS and ACP token, at the beginning and at the end of each window. And then I also need to add padding for the final batch. That is, the last window will be shorter than 512, so I need to add padding to make it equal to 512. And yeah, so that's pretty much the plan. So just start the function. I'm trying to name it as explicitly as possible, the function name, and so this will become a little larger. I mean, the function name. Chunk text to window size and predict proba. And it will take input IDs and net. First, initialize empty list of probabilities. This is the final return variable that I'm going to return from this function. List equal to an empty list. So just like before, I will have a start and end position and also a window length. And my starting position will, so the starting position will start from 0, and the first ending position will be start plus window length. And then after one loop, I will update both the start and end again, because as a window slides forward, the second starting position will be the previous ending position. So it's just a sliding window mechanism that probably many of you have used in other kind of situation. And I'm choosing here 510 and not 512, because as we discussed that FinBERT takes max token length of 512, but I'm skipping space for the two special token. That is, at the beginning I have to attach a CLS special token, and at the end I have to attach a separator special token, that is ACP. So the window length will be 5110, and my loop is a boolean variable, and start it with true. And now I am starting the loop. End position is start plus window length. Now if end is more or equal to total length, I think we have already defined the total length here, right? What is a total length? Yeah, that's a 1. Let's just put it as a argument to this method. Okay. In that case, I have to stop the loop, false, and also end. Okay. Now that's where, now here I have the actual steps starting. So first I need to extract the input ID chunk and the attention mask chunk, then add the separator and the classifier special token, and ultimately get the, and also I need to add the padding and ultimately get the probabilities by feeding the model with the input tokens and attention mask. Yeah, so let's start. The first is step 1, which is define the chunk. Input IDs. I need to grab the items from the input IDs list, starting from the start position and up to the end, that is with a slice notation. And similarly, attention mask will be mask start to end. Okay, that was step number 1. Step number 2 is to add the CLS, append CLS, and input IDs chunk. So for appending the CLS, we already discussed that the class ID for the CLS token in FinBERT is 101. And because input ID is a list of all the class ID, so I have to, there is nothing called CLS or SCP for FinBERT to recognize. For FinBERT model to recognize, I need to pass the relevant class ID. That's how it works. Input IDs chunk plus, and the class ID for SCP token is 102. And I need to do the same for attention mask, but for the attention mask it's slightly different, because attention mask will not have CLS or separated token. Instead they will have 1 in those places. That 1 means they need to be given attention, basically, because attention mask is just for masking. Attention mask chunk plus 2, sorry, plus 1 again. Okay, that was my step number 2. And step number 3 is I just want to define a dict, so that so basically I am converting the PyTorch tensor to a dictionary format, as they need to be in tensor form rather than Python list. And here I'm also going to convert to correct data type, which is long for the input IDs, and for the attention mask is the int data type. So convert to dict, convert PyTorch tensor to dict. I'm defining a new dictionary here, input dict equal to torch.tensor. Yeah. So I'm converting. I think it is opposite what I wrote here. That is, I need to convert the list to a PyTorch tensor, because remember we just discussed earlier when we were tokenizing right at the very top. Where did we tokenize? Let's see. Yeah, here. So when we are tokenizing with the tokenizer.encode plus, I did not pass any return tensor, and that means the return keys and the return vector will just be a Python list. That will not be a PyTorch tensor with the gradient tree, etc. And we also checked that by doing this line, that is type of tokens input IDs. That's just a list. It is not a PyTorch tensor. But for passing these input ID to the model as the input numerical array, I cannot pass a list. I need to pass a PyTorch tensor because the model will need the gradient tree calculation to be done. And hence, just as we discussed earlier, that later we will be converting our list to tensor, and that's what I am doing here. So converting my converting regular Python list to PyTorch tensor. Yeah, so torch.tensor, to that I pass input IDs chunk and convert it to long format. Similarly, I need attention mask, and that will also be torch.tensor and attention mask chunk dot, this is of type int. Okay, and what is left is I need to just now invoke or execute my model. So outputs model, we already have the model defined, so I can just pass it input dict, and that should give me my logits. But so these outputs are actually logits, and I need to convert them to probabilities by using softmax. PIL probabilities equal to torch.nn.functional, dot softmax outputs 0. And finally, I need to update my probability list. We defined the probability list right here, and that's the variable that I'm going to return from this whole method. So let's update that probability list. And now I'm just going to execute this function. Chunk text window size. To that I pass input mask, and also the, what was that? I think that's the total length of my tokens. And when I printed this probability list, this is the output that I got, and this is a PyTorch tensor. And here, each of these tensor actually represent a sentiment score for that particular section of the text. And why did I get 4 of them? Because my long text was divided into 4 segments, and each has a length of 512 tokens. So that's how I got the sentiment score. And of course, I need to apply argmax method on these arrays, individual arrays, to get the actual sentiment classification for that section of the text, that is for that chunk of the text. So let's continue doing our work here. And actually, for my case, I am going to calculate an average sentiment for the entire text, right? Because that's what we want. We can actually calculate the sentiments of the 4 different chunk or 4 different segment of the long text. But what we want is which was the purpose of the video, that how to deal with long text when applying BERT. So for my entire text, that is this whole text, I want to capture or get a single sentiment, and for that I need to get an average. So yeah, so let's do that. So pretty much I'm going to stack those individual returned tensor and then get the average sentiment across the full stack, full text. So my stacks will be torch.stack probabilist, and if I print stacks here, so these stacks are just a stacking of all the individual probabilist, and let's see the output. So this is the output that I got from the stacks, and we can see here. So this is the stack on which I need to get the mean value to get my actual sentiment score, that is positive, negative, or neutral sentiment, because FinBERT has this 3 sentiment score, 0, 1, and 2. And what I see here, that I cannot directly apply the mean because this is a 3-dimensional tensor. But as you can see, the probabilist is a 2-dimensional tensor. Because of this reason, I need to reshape it first. So if you just check the shape like this, shape equal to stack.shape, and then HAPE, the shape will be this 413. So this is the problem here. So I need to reshape it, and for reshaping I can use this one. It is a PyTorch tensor, so I can use torch.reshape. Remember, I cannot just directly use the normal Python or NumPy method of resize here, because this these stacks tensor right here has a gradient attached to it. So directly applying the resize method of Python or NumPy will give you a runtime error saying that the resize variable requires we are trying to resize a variable that requires a grad. So I need to use torch.reshape if I want to keep the gradient. But in a second we will see that from here on I no more need to keep the gradients actually, because I'm just doing inferencing. I'm not doing any training further, so I can actually get rid of the gradient. But first check torch.reshape what kind of output it gives. TSDK first the tensor and then the 2 size that I want to give, and that should be in a form of tuple. Shape 0 I want to keep, and shape 2 I want to keep. And when you run this, you get this tensor right here. Torch.reshape stacks shape 0 shape 2 will give you this tensor, which is 2-dimensional, which is what I needed before I apply mean method on them. And see that the return of this method also has a grad function. That means this tensor has all the gradients attached to it, and hence what I'm going to do, I'm going to define a utility function where I can get rid of the gradients. But first again, check the shape of the probability list. That's this tensor. Right, it has 2-dimensional. Okay, let's write now a util function so that I can do 3. This util function I'm going to do 3 things. First, define a context manager with torch.noGrad, then get my stack from the probability list, then resize that stack and finally calculate the mean. Okay, so I'm just doing stacks equal to. So these steps, we already did it previously, but I'm just including everything within a single util function so that I can reuse that again. Torch.stack probability list. Next is to resize them. Stacks, and now I'm going to use the normal resize method because now I am within the context manager of torch.nograd, so I do not need to use specific PyTorch specific method. I can just use stacks dot resize shape 0. Sorry, this says and list, and also stacks dot shape 2, and finally calculate the mean. There will be a S here. Mean will be just stacks dot mean, and across a dim, across each across a row, so dim equal to 0. Return mean. Cool. And then execute this function. So my mean will be get mean from proba. To that I pass the proba list. And when I execute this function, I get this output. Let's see. Oh yeah, I need to actually apply the torch.argmax. Actually, this mean variable will give you an output like this. So this is a value of this mean variable, which is a tensor, and it gives the individual scores. Now I need to apply the argmax to get my actual ultimately sentiment classification. So for the entire text, of course. So torch.argmax, just pass the mean variable, and then get the item. And that will give you the values, and when you run that, you will get this 2. So what is 2? 2 in the, and to understand the 2 here in FinBERT, I just went to the official documentation of HuggingFace for FinBERT. This is that page, and you go to files and folders and look at config.json, and here they have given these labels, id to labels. So a label of 2, that means it's a neutral. And that's what we got. That is torch.argmax gave us 2. That is the sentiment of the whole text is neutral. So this overall text. So in summary, what we did again, we just chunked the entire text into different segments so that no segment crosses more than 512 tokens, then calculated our sentiments on each individual chunk of the text, and after that we stacked those individual tensor, that is from the model output, and applied mean on the stacked or combined tensor to get the overall sentiment score for the entire text. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button, and also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So see you in the next one. Thank you very much for watching. Hey everyone, this video is continuation, or rather part 2 of a previous video that I did just 2 days before of getting the sentiment classification using FinBERT on a long corpus of text. And the main problem that I dealt with there is that FinBERT or BERT in general has a token limitation length of maximum 512. That is, it can accept tokens or text whose tokens has a maximum length of 512. So what will we do when we have a text corpus, long text corpus, where the token length is much larger than 512? So this was a problem we dealt with in the previous video, and a solution technique was that I used a sliding window. That is, I chunked the whole text into 512 segments and then slided the whole window over the entire text. And for each window, I got a classification, that is sentiment classification, applying FinBERT, and then I took a mean or average over all the prediction for all the individual window, and that mean prediction or the mean classification is the final classification or sentiment classification for the whole corpus of text. So that's how we dealt with the problem of handling large token length text. And in this video, it will be a small change only, where instead of using various other normal Python splitting of the whole text, I will be using a method specific to PyTorch to split the whole text into different window and then get the mean prediction. So that's the only kind of change in this video over the previous one, that is part 1, and otherwise the overall approach to handling the problem remains the same. Let's start. Note, in the previous part 1 of this video, when I was using pure Python way of splitting the text, I did not use this part, return tensor pt, because in that case, so that means that if I don't use this return tensor equal to pt, then these tokens will just be a normal Python list, and that will not be a PyTorch tensor. And that was a reason in the part 1 of this video I had to convert the list back into PyTorch again before the final steps. But now in this video, I'm going to use right from these steps, this return tensor equal to pt. That means I am going to get back as my tokens a whole fully PyTorch tensor. So I do not have to go back and forth between Python list and PyTorch tensor in here, and that's the main benefit of handling the whole problem with PyTorch. So that's my tokens, and okay, and I'm just going to print my tokens and also print len of tokens. Let's run this notebook. And after running this cell, I get this output. Definitely this has been truncated. What mainly it is showing that these tokens is a dict with input IDs, token type IDs, and attention mask. And here this tensor, actually input IDs is a two-dimensional tensor. Actually it has been truncated, and attention mask is also a two-dimensional tensor which has been truncated here. So what I want to do right now is to apply the windowing technique over this tensor of input IDs and also attention mask. That is, I'm going to build one single window, or rather multiple windows, where each window is of a token length of 512, and then get as many windows as possible. Obviously the last window may be lesser than 512, and where I have to use padding to fill up the leftover places. So basically it is the same approach I am taking here, what I did with the previous video, that is part 1 here. So only change is that in the previous video I used plain Python to make these windows, and here I'm going to use PyTorch split method to split this entire long tokens, so that I do not have to again transform my list into tensor down in the notebook, because in the previous video where I got Python list and then later I had to transform again to PyTorch tensor, those kind of back and forth calculation is not needed here, because here I am only working with PyTorch tensor. Now about the split method, let's quickly go over the documentation in PyTorch. So this is the method that I'm going to use, and it splits the tensor into chunks. Each chunk is a view of the original tensor. And what it does is that, for example, I have an original tensor A, which has 7 elements, and we can say it's a two-dimensional tensor. And then I apply torch.split on this original tensor with a number of split of 2, and I get a result where I get a split or chunks where each chunk has 2 elements. This has two elements, and the last one obviously has a last leftover because it has only 7 elements in the original tensor. Okay, so this is the one that I'm going to use. Before that, quickly check the length of the input IDs. And because this is a list of lists, so I'm going to use a 0 over here. Yeah. Okay, so we have 1653 as the total token length of this entire text, and obviously that's what the problem is. That is, FinBERT or BERT in general cannot accept this whole token as it is, because 512 is the limit, and that's the whole reason that I need to split it into window of 512. So yeah, next input ID. And just like the previous video, I'm using 510 because I need to keep 2 places for the 2 spatial token called CLS and ACP at the beginning and at the end of each chunk. So those 2 I'm going to add later after this line is over. And just like this, I need to do it for attention mask as well. Okay. Cool. Yeah. Can I check the length here? Let's try. Attention mask chunks. 1 second. This has a different meaning. Let me clarify. So if I print these attention mask chunks, I got the length of attention mask as 4 because when I print the entire tensor, I got this tensor. And obviously it is not showing the entire thing because it's full output data in a text editor. Yeah, so when I open that entire tensor in a text editor, this is a long tensor I get. And what you see is that the original total text has been split now into 4 different parts. And this is the first window, then this is the second window, this is the third, and the last one is a leftover. So, and each the first 3 windows should be each one should be 510 because that's what I mentioned here when I was splitting it. Split 510. And you can check that actually by just doing this length of attention mask chunk 0, and that should give you 510. Yep. All right, now. Okay, that was just splitting it into 510, and now it's time to add my CLS and separator token. And we already discussed the CLS class ID is 101 and separator, that is the ACP class ID, is 102. And I am going to use torch.cat, which to concatenate these two to the beginning and end of each of these 510 tokens. But all these things I'm going to do with a single util function. So let's start writing my method where I will be doing all these mechanisms. Tokens. I need to take the input IDs. Just like before, we need to take the 0th index, and then on top of that, I need to apply the split method. Split should be 510, what we saw here. But now here I'm going to use actually I could use 510, but I'm just going to use chunk size minus 2 to be explicit about what I'm doing here, that I'm keeping 2 for the 2 special tokens. Do the same for my attention mask. Oh, yeah, sorry. I need to change this here as well. Now I'm going to start a loop for our previously we already have calculated what is this input ID chunks. So I'm going to run a loop for the length of these input ID chunks. For I add the it's time to add the special token of CLS and separator to these input IDs. So torch.cat. The first one would be torch.tensor. That's for the CLS token. Then next one is just input ID chunks I. Last one is for the separated token, that's torch.tensor. (102). Okay, similar operation I need to do for the attention mask, but for the case of attention mask, it's not, instead of CLS and the separator token, I just need to add the class ID of 1. So attention chunks I. Yep. All right, now I still need to add the padding to our tensors to push them up to a length of 512, and this padding should only be required for the final chunk. So to do this, I am going to bring in an if-else statement that checks if the tensor length requires padding, and if so, then add the correct amount of padding. So let's see. So my boolean variable right now here will be not boolean actually, it's just a variable for controlling my if-else statement. So pad length should be chunk size id chunks I dot shape 0. Why I'm taking this? Because we have already seen for any particular element of input id chunks dot shape, that will give me the size. And the size here before this method is 512, but after here in this method by at this line it will be 512 because I have already added the CLS and SCP token. Now this pad length will be required only for the last tensor, but anyway I'm checking it for every turn in the loop, that is for every iteration in the loop with this I here. So for except for the last chunk, this pad length will be 0, but for the last chunk this pad length will be greater than 0, and that's why my if else statement will be pad length. Only then I need to add the pad, so that means input id input id chunks I. Same technique, I'm just doing torch dot concatenation I torch dot tensor. I need to add a 0 for all these positions, so 0 multiplied by pad length. Yeah. And I need to do the same for the attention mask as well. Mask. Let's copy it. Why it's saying not defined? Let me say attention mask chunks. Anyway. Okay. And here. Yep. Finally, return id chunks and attention mask chunks. Yep. Oops, sorry. Okay, now in my next sentence, I'm just get yeah, and so up to this time, everything looks all right, and now I need to define a dict because in the finals, that's the final step, and this dict will just follow the style of FinBERT. Because we know FinBERT, we already saw that tokens has these key, this dict format, which has a key of input IDs and attention mask. So I'm just stacking all these individual tensor with torch.stack. Similarly, attention. Okay. Attention mask chunks. Yeah. So this is like the combined after stacking. This input ID and attention mask is the has all the tensor stacked together. And now defining a dict called input dict. Input ID should be in the long format, so I need to do input ids.long and attention mask should be in int format. Yeah. Just want to print this and see everything is just working right. Yeah, looks all right here. And yeah, I just want to check another thing, the length of this. And here is the shape, and that's exactly the shape I wanted it, because and I can also check. Let me check input dict attention mask dot shp. Yeah. So now this shows that this is exactly the shape which will be acceptable by FinBERT, because I have the max token length of 512, which is what FinBERT expects, and this is also called the sequence length. And the 4 here is just a batch size. Why? Because our entire all tokens have been divided or split or chunked into these 512 segments each. So yeah, so that's a shape I needed. So yeah, now I can just invoke my model to get my outputs. Outputs equal to model. We already defined the model. Input dict. This model, these outputs are actually the actual logits value before softmax, and to get the probabilities I need to apply softmax. Puts 0 dim equal to -1. The spelling mistake. Let me correct it. Probabilities here. And then mean probabilities, because I also need to I have already explained in the part 1 that after I get the probabilities, I need to get the mean, because that's the whole purpose, that from these probabilities I can get individual chunks classification score, or the probabilities or classification label, but I need for the whole text, and for that I am going to get the mean probabilities, and from that mean probabilities I will apply argmax to get the classification for the entire text. That's the whole purpose of this problem. That is, even though I have much larger token size, but I divided into 512 token and then got the individual probabilities for the individual chunks. But at the end, I'm getting the mean to get my whole text classification score. Mean probabilities. PRLITIES. That would be probabilities dot mean across dim of 0. Let me just print this. It will, yeah, okay. Fantastic. So this is the mean probabilities for the 3 labels. FinBERT has 3 labels, 0, 1, 2, and that's actually for negative, positive, and neutral sentiment. Now I need to apply the argmax to get the ultimate single classification for the entire text. So torch.argmax probabilities dot item, and that gives me 2, which is exactly what I got in part 1 as well when I was doing in Python. And this 2 means that it's a neutral sentiment for the entire text. And what was my text? This is the text that I have taken from this link right here. It's about some crypto's regulatory market report, etc. So yeah, that pretty much wraps up this video. So in summary again, that I just the problem that was solved in this video is to handle text which is much longer than 512 tokens, because 512 token is the limit of FinBERT or BERT, but we handle that problem by taking a longer text and split that text into different segment, and ultimately got the mean sentiment score for the entire text. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So see you in the next one. Thank you very much for watching.